started in the geophysics. I started in airborne EM onshore. I then went to airborne magnetics and radiometrics acquisition. I ran the gravity group at GA for some time, and then I moved into the petroleum marine section of then BMR, now Geoscience Australia, and was working in their basin analysis group for many years.
Mike, just so people understand, that wasn't last week, right? How many years ago was that? And was this open? Is that sort of petroleum-based experience? Was that to open up new basins for prospectivity and investment?
Yeah, the GA's role is to assess access basins on the Australian continental shelf, and then to bring new ground to the market. And so we undertook, a lot of it was acquiring new seismic data in greenfields areas where nothing had been acquired before. Get flying aeromagnetics, working with gravity data. And then we also did some other work. I started in the late 1990s.
When I finished.
So basically I've been looking at the use of potential fields in specifically the petroleum's area since the last century. There you go.
Yeah, that's right. So the challenges for Australia with opening up acreage were the complexity of basalts, interbedded basalts within the sedimentary sequence, high amounts of gas, and operating in quite complicated waters. International waters, well, not international, between East Timor, for example, and Australia, between Papua New Guinea and Australia, between New Zealand and Australia, same sort of thing. They're very rough seas, very complicated to acquire seismic in 30-foot waves. It's a bit more complicated. Anyway, sorry, Mike, go ahead.
Okay, so I have basically constructed this PowerPoint and presentation without using any formulas or mathematics. I've tried to keep it all out of it. I consider the geologists, it was the last thing you needed to see. So I'm basically going to go through.
Thank you. I told you he was a nice geophysicist.
I'm just going through this in terms of what's here on the screen. So looking at why we use potential fields, what they are, why we and how we do the filtering, image processing, which is important, having a look at interpretation, some of the depth estimation methods, looking at what the difference between normal potential field data and gradient data is, having a look at a bit of a delve into the FTG data, and then how we use it, and then some data-driven interpretation with WormE, and then Jeff is going to present some work on the Couchy the new Couchy work we've been doing.
Now, if that agenda, like if we need to, for example, like that agenda, if you go back to that agenda.
Yeah.
So if there are things that are missing, so I know that there are questions that both BICEP and Petronas have. We just need to lock in a period. Maybe we'll spend most of tomorrow on Couchy and questions and answers, like your top. I think there's a mixture of Malacca Strait specific questions, and then there are sets of questions that maybe are on adjacent basins or adjacent areas, like on understanding regional tectonics and older geological fragments, and maybe how we reckon. You can pose questions and we can give you alternate perspectives on how to address your problem, because it may or may not be related to necessarily FTG or like other methodologies that you'll be well aware of, but from our experience, what works and what doesn't work.
You do have our data, the interpreted data from Selat Melaka.
From which block?
Selat Melaka, the one that we gave you guys to work on. You have
Malacca Straits. We have that, yes.
So we can have our discussion on that.
Yep.
Because basically what we wanted to do is to understand how much we can extract out of the FTG, out of the interpretation that you guys have done for
Yep.
us. Yeah,
Excellent.
to get a better understanding on how to use data.
Correct, because
I think from what you're saying, this will in some ways help, because what I've tried to do is it's very much, I suppose, my way of how I look at data and how I use data. And I hope that this sort of gives you a scope of what can be done with this data.
excellent. All right.
All right, we'll get.
Oh, yeah, sorry. Yes.
So in our other project, we use also FTG data, and then they use a so-called like Euler decomposition. Yeah, and they can highlight some of the features potentially to be carbonates.
Yep.
So I would like to know, is there any potential in Selat Melaka as well? If you can touch on that, on how Euler decon works and how it can, detect the potential carbonates. So maybe in Selat Melaka, if we have the chance, so we would like to see that as well.
Yep, extracting specific geology out of the geophysics is possible, and I think that's what was done as well. But we'll touch on that.
Thank you.
All right.
Oh, by the way, can we have the PowerPoint in in a PDF?
Yeah, of course.
If you don't mind.
No, that's fine.
Everything except the last one.
It's easier for at least for me to scribble on.
So, Mike, have you got a PDF?
Yeah, if you can give it to me now, I can just scribble on it.
Can you share from the talk?
No. As in.
You wanna do the talk? Yeah, I'm trying now.
So, do you want access to it?
Yes, I'm trying.
Hang on, Cedar. I'll just send up the very latest version I've got here.
So you're going to email it?
I'm just going to put it on the server.
Okay.
If you got access to the server from there.
I do. Cedar doesn't.
I will do.
Hang on, I'm just.
That's a good point.
So it's easier for me to just
write
scribble
notes.
on it.
Yeah.
Hang on.
Do you want me to? I can do it on my laptop if you want.
Actually, yes.
Well, it won't be configured for you though.
I can use from there too.
Yeah, I'll just stop sharing because I've got to muck around here for a minute.
If you go to server, it will be work.
It doesn't have a VPN connection. So I can't get onto the.
Yeah.
My account has VPN.
Yeah. Okay. Let's do it on your account.
Do you want me to just do it?
Mike, why don't you start, because we'll catch up and distribute the PDF in a.
Oh, I'll just save this and get it going, because otherwise it'll take some while to.
Oh,
Okay.
or later on you can share.
You're connected?
Share to me through WhatsApp. I can just.
Yeah, that's cool.
Share to them in the group.
Perfect idea, Sean. Before we get started, bathroom stop. Anything you need, let me know.
Mike, where did you put it? In?
I'm getting there. Hang on.
Okay.
Does anyone want a cup of coffee?
Okay.
Got a cup of coffee?
I will be happy if you put it to the technical.
In technical.
Yes.
Where in technical? Just
Root directory.
okay. Okay, there you go. The snail is on its way. And back up.
Mike, Did you choose any folder? Did you choose any folder in technical?
Yeah, it's in technical. It's just going straight into the top of technical. Petronas FTG workshop.
Yep, I got it.
It's 140 slides just to be annoying.
Oh,
40.
40.
Don't worry. I know better.
I never thought Australia is like that huge. I mean,
Oh,
It is.
it's huge, and everyone. So like everyone lives. Sorry, shouldn't touch the screen. Everyone lives, along the edge of the water. And basically once you get to this point, it becomes this way. It becomes very like this. No, it's just country farmland.
No wonder there's no crashing wave.
Yeah, that's
Every
right.
day, because
Exactly.
We are in,
it's an embayment.
we are in the
Yeah,
bay.
correct.
I'm ready to
Correct.
start when anybody is.
Mike, one more question.
I would be
Yeah.
very
And this
interested.
is I'll show you over
Technical now,
here
because I cannot go into the
Um,
presentation.
is where they found hydrogen.
It's not there yet.
Natural
Oh,
hydrogen.
yeah, okay.
It's 600 megabytes, and
Very, very
there's
fascinated with
it's still got
hydrogen
to
generation.
get there.
There's a basin. There's a basin up here called
Naturally.
Amadeus Basin. It's got a salt basin,
Yeah.
and it has. When the petroleum guys were drilling, they got 8% helium. So helium's worth more than oil.
So basically, this is the intracraton.
Yeah, but basically you have Centralian Basin. So this is the Canning Basin up here, and then all this is very old geology.
Yeah.
Like it's all billion-year-old. So obviously all
Archean.
Yeah.
Archean.
Yeah.
Archean.
But there's some fascinating geology in here. Lots of salt plays and complicated petroleum. Anyway, all right, Mike.
Yeah, like
Okay. It's on its way,
So
Cedar.
Mike, 140 slides is a lot. You're probably going to make everyone just maybe don't go too heavy.
Oh no, it's not. A lot of them's pictures.
Oh, good.
Lots of
As long as they're
pictures.
coloured, I'm happy.
okay.
Coloured pictures.
Lots of examples. That's good.
Yes. Okay. Why do we use potential fields? This guy Patterson was one of the pioneers of geophysics in modern geophysical use in the world, and he considered that the magnetometer survey was just as much a way of mapping geology as an air photo and surface traverses, and it's probably better than an air photo because most of Australia is covered with sand and dirt, so we can't even actually see the geology. So this is the Australia. That's why we put so much work into covering the Australian continent with gravity and magnetics and radiometrics, so that we can actually see the geology through cover. Now I get into some terminology. Potential field. Okay, it's a force field where the value at a position within the field is only dependent on the position. So if we get a bunch of nice young people to go diving, and they start at the pool side and go up to the various different platforms and all jump off, they've done different amounts of work, they've traveled a different path, but when they get back out of the pool, they've all got exactly the same potential energy again. So it doesn't depend on how you get there or how long it took you to get there. It only depends on your position within the field. So it's an important thing that makes it useful and easy to use.
When you say position, so
in three-dimensional space.
Okay. So in terms of the pool here on the picture, it's the distance from mid-sea level.
From the level to the pool. So if you get to the 10-meter platform,
so
you have a higher potential energy than if you're on the 3-meter platform.
Okay.
But once you've done your dive, even though you've done all that work to get up there and come down again, that's it. Your potential energy goes back to zero because that's what it is at the bottom at the pool. So whenever Cedar, it's there now. So whenever we're talking about a potential field, we only have to worry about, in terms of the value that we are measuring, we only have to worry about that it's the value at that position. That's where we get the the number from. Now, the mathematics that covers this was put together originally by 18th century French mathematician Laplace and Poisson and Cauchy. If you want to look up what they actually did, it's all on Wikipedia. But these especially Laplace and Poisson, cover most of the mathematics, the basal mathematics for potential fields. Cauchy is what we're using as a mathematical method that allows us to do what we do with new work with downward continuation. If I talk about a platform, that's the platform we're doing the measurement on, which is like aircraft, ships, drone, or on the ground. And sometimes in geophysics, we use derivative and gradient. They're equivalent terms. They're a calculated rate of change in a value. So that if derivative, gradient, it's the same thing. Exploration undercover, why we use potential fields. It's low cost especially compared to seismic and drilling. Airborne surveys can provide a consistent, high quality and continuous coverage. That's the big benefit of the airborne coverages, is that you get a continuous, consistent data set in plan. And it works from the target scale for fully continental scale. It's a very mature methodology for extracting geological information from a geophysical signal that's been worked on over many years. I mean, the other thing is success shows that it works. It's just the history of potential fields data and mineral and petroleum exploration. And it includes the magnetics, gravity, gradiometry, and electromagnetic methods. So CSEM is a potential fields method.
What is the difference between gravity and gravity gradiometry?
That's what we're going to talk about.
All right.
Gravity is measuring the simple acceleration due to gravity at a point, and the gradiometry is measuring the gradients, the rate of change at that point.
Rate of change.
Okay, we'll go
In different directions.
Different directions. So we'll get to that.
Oh, Dr. Zuhar has joined us.
Okay.
MRT.
Everyone's working here, Dr. Zuhar. They've all been very good. They've arrived on time. And just to add to what Mike said there, like whenever you're working in a basin, you define a geological framework. You define what I would call a potential field framework and a seismic sequence stratigraphy framework, like the whole or the chronology of everything. So the idea is to be able to place each data-driven solution into a framework. So therefore you can compare the different geophysics or different geoscience data to your problem. The trick with it is to have it in a form that you can use logically with each of the other geoscience data sets.
I have a question.
Yes.
So we have airborne and shipborne gravity and magnetic. Do we have shipborne FTG as well?
No,
No.
it's only airborne.
Airborne.
But sorry, go ahead, Bob.
Oh, there probably will be shipborne stuff that actually, there would have been ships, international science ships that went through the Malacca Straits and had their magnetometers and gravity meters on, but it would only be in Traverses as they went through there.
But it won't be tensor gradiometry.
No, it won't be any of that.
So one of the things that Intrepid Geophysics and Geoscience Australia has been doing is integrating the marine gravity, ground gravity, and the airborne gravity. It's a bit of a science, quite complicated integrating, because you're getting data sets from traveling through an ocean to onshore to airborne. Obviously, airborne data is a bit more coherent and reliable and predictable.
Okay, so in basin analysis, this is a very simplistic slide. The attributes that we're trying to find and define: the container, the history, geometry, subsidence history, petroleum system, and we have very limited data sources. So we have basically from the most expensive to the top down, drilling, seismic survey sampling, potential field surveys. And the key to all of this is data synthesis. Now, this comes into what platform we're going to do this work on, but it does become the need for a three-dimensional platform, because we're looking at seismic data, which is in the vertical plane, and the potential field data is mainly in the horizontal plane, except for the couchy stuff, which is now in the vertical plane as well. Now, at the bottom there, there's evaluating trap integrity in this Timor Sea. This is the first job I worked on with trying to, we were looking for seepage studies. So that was an integration of seaborne sniffer technology, where we had a fish towed behind the ship. Seawater was pumped up into a gas chromatograph to measure the concentrations of hydrocarbons in the water. We also was flown over there some detailed aeromagnetics. We're looking for where areas of whether there was a hydrocarbon related magnetic deposits due to seepage. And we could find that where we look at a trap and that was magnetic. Basically, if it was a magnetic fault adjoining that trap, basically you knew that most of the hydrocarbons had seeped out. So
Mike, when you said high, like what resolution magnetic data did you need?
We were flying, they were flying 100-meter line spacing in 100 meters of water. So this stuff with the trouble with the Timor Sea and the Vulcan subbasins up there is the reactivation of the faults that all got bent again, and caused the traps to open, some of the traps to open up, and you got leakage. But that leakage led to the deposition of magnetic minerals, and we could see those in the aeromagnetics, and it correlated with the sniffer anomalies where you're getting leakage on surface faults. So that was work I did, basically last century. So here's just, again, a simple first approach of some of the basin attributes and what we can get at with the potential field data. Composition, rock properties, volcanics is very important in the Australian area. We have a lot of volcanic margins, and that was a major part of the work. Use of integration of satellite gravity into the shipborne gravity was a big part of the work, and looking at composition of rocks and structure, especially when we're having sparse two-dimensional 2D seismic, and trying to work out, help the seismic interpreters with strike directions and what, trying to join faults in one seismic line to another fault. Which fault does it join in the next seismic line?
So one of the things Intrepid over the years has been trying to do is to get rid of the geophysicists, so because they're too difficult to deal with. So we've developed technology that basically automates a lot of the geophysics and assists in extracting geology from geophysics.
So in terms of rock properties, what you can differentiate?
Sorry, I did. What was that?
In terms of rock properties, what can FTG catch or differentiate?
So the question is, Mike, in terms of rock properties, what rock properties can be extracted from potential field data? And
it's basically that comes from inversion. Okay, and there are ways we can solve by mixing gravity and magnetics together. You can solve for magnetization density ratios, and the inversion system gives you a distribution of density and a distribution of magnetization, and that's a bit, again, that comes down to the thing. One of the underlying principles that need to be remembered is when we're doing any work with potential fields and we come up with a solution, that solution is non-unique. The mathematics says that you can't, if you do an inversion, The inversion is a likely, given all of the data that you have, the probably a good fit to that data, but is not the only fit. So this, it's a tricky one.
It's the most likely model, right?
It's the most likely model.
So that just to
But
take
there's
this,
always, you can make another model.
so to take this further and put it really in petroleum terms, what you'll see in some of the catchy work that we've done elsewhere, we think you can identify the presence of gas with FTG, but it's never been published. We've got
Gas in FTG.
Yeah. So we tomorrow morning we'll show some examples that identify not just depth to geometry, but also the FTG data seems to be responding to the presence of gas.
That's because of the density difference.
Correct. Very interesting. It's a very, let's just say it's right on the edge of new science, right? We haven't published it yet, but we've been working on that and we've applied it in Sarawak. So it's as far as rock properties go, yes, and theoretically, pore, the composition of the pore space, a bit like in fact AVO.
Is this more of field size like or
The scale.
regional? Yeah.
So it depends on the process and the data set. Obviously, if you've got data that's 1.5 kilometers spaced between the lines and 50 meters spacing along the line, that gives you an estimate of the fidelity of the data. Obviously, if you have magnetic data at 25 meters spacing, it's all and 3 meters, you can get a lot more detail. So for a basin scale project, FTG, I think it's 1,500 meters is suitable, but you can acquire FTG data at closer line spacing to give you greater confidence. Because whenever you're interpreting something, it's really, really important that, like in the seismic world, you never interpret one seismic line, you always interpret a group. Similarly, in potential field analysis and interpretation, because you're looking at a map, you can see the geometries and how they change in the structure and where the lows and highs are. So it depends on the scale of the structure. That's what relates to, you know, the design of the survey. So when you're designing a survey, you design it to fix a problem. When you're acquiring seismic, you're acquiring it, for example, you're acquiring the seismic at a particular depth. So the old Malacca Strait seismic may well have never been able to image anything deeper because it was designed for a reservoir level depth of 1.5 Ks or something like that. So, you know, the data, you've got to let the data speak to you, but you also have to understand why the data was collected and what purpose. And that's quite often lost over time.
I'm very interested in the slide before. We can actually define volcanics from Cauchy.
Good.
How good are we at that? I mean, how mature is the science?
In terms of looking for volcanics and looking at sills and dikes from normal magnetics, that's very mature.
I'm talking about
No,
I'm talking about differentiating volcanics from carbonates.
if there is a distinct difference in magnetic susceptibility, then that's entirely able to do that.
So for example, the Cochrane High in Sarawak, right? I have to talk in my nomenclature, so about the 2020 pick is a tombstone carbonate. Right? When I say tombstone, I mean a very ultra hard one. You know, that versus a ferruginous limestone that you might get in the Canning Basin where it's all iron oxidized, the potential field response will be quite different. And when you have a carbonate that's on a stable platform, and as it goes away from being stable, it becomes less competent and more marly and soft. So the challenge with potential field data, like one unit as you go along, can change from being magnetic to not to being non-magnetic. That's why potential field data works really well with seismic, right? Because you get insight from the seismic sequence stratigraphy, and you get insight on how continuous and the rock properties from the potential field data. That's why the Cauchy solution is so good, because you can stack data up against each other and overlay it.
We got problems in ultra deep water in Sabah, trying to differentiate between volcanics and carbonates.
It shouldn't be. It's quite. I mean, if they're both fast, like 6,000 meters a second, but the style and the characteristics of volcanics versus carbonates should, I mean, both from the rock properties that Mike's talking about, but also the characteristics of the textures of a volcanic unit versus the textures of a carbonate should be different. Like the way they're deposited, the geometries, all those sort of things should stand out reasonably well. But if they're at the depth, like for example in the Sabah area, I don't know where in the sequence, but you're talking about, but generally speaking, it's all covered by 3D seismic, right? And you've got issues with gas and believing what you're looking at. If it's in the accretionary prison, it's really hard, like away from the fold belt, because it's just, is it the Crocker formation that's driving, the big injection structures? And
I think what Zul is mentioning is about East Sabah, is it so?
East Sabah.
No, not really. East
Near
Sabah.
shore?
The carbonate
Platform.
Sorry?
Sabah platform.
Oh, Sabah platform.
Oh, way out in the, so
Also
I know that area well. So
Yeah, you guys had
Yeah.
some.
So you can get the carbonate style of deposition. So you can, in that area, the geology is very simple. Sort of.
You guys were dealing more on the toe thrust.
Yeah, you do remember.
This is
No, but when we did the
way
work
out towards the
We-
international border.
in very complicated politics.
Yes, let's not dwell about that.
I didn't say anything.
Yeah,
Um,
but we have seen some good discoveries in what we believed before as volcanics. It turns out to be Oligocene carbonates.
Yep.
And we are looking at the older Eocene carbonates. But the problem is always trying to differentiate between the carbonates itself and volcanics, because we know there are volcanics there.
Yeah, and the way they deposit and the extent and the geometries.
It's very much isolated.
Yeah.
And some of these carbonates are usually they build up on top of
The
existing
volcanics as well.
volcanics.
Yeah.
Exactly. So how can we differentiate? Because on seismic, you can't really differentiate.
No, but if you were to use.
I've got some slides a bit later on that'll show you.
Okay,
how that
we'll
works.
Okay, that'll be great. That'll be great.
Sorry, Mike, you're gonna have to cut us off from discussion.
Yes.
Yeah, I know. I'm going to tell you.
But
All right, so the dense potential fields, how they created, the density and magnetism of material in 3D space produces them. The forces and mag are examples of potential fields. So they satisfy various important mathematical functions that were developed by Laplace and Poisson and others, and they provide the basis of what we can do. All the filtering, the manipulations are based on this mathematics. Okay, the observations are done indirectly using gravity meters and magnetometers. And the thing to remember with gravity and magnetic fields are they integrative fields. So they sum all of the source signals from all of the sources together. And this is a whole lot of why the filtering work, we have to pull it all apart. The other interesting thing is in terms of fall off of signal. So gravity, normal gravity, which is GZ or TZ in the FTG falls off at 1 on R squared. And if you take the first vertical derivative of that GZZ, that goes at 1 on R3, which is the same fall off as magnetics. So I tend to always be comparing especially with the FTG, the TZZ or GZZ with the magnetics, and you're actually starting to look at the same sort of frequency content of the two fields. Acquisition, I'm not going to go into a great deal about acquisition. The main thing is we when acquiring this data, we acquire the whole world field. There's regional global signals, there's time varying signals. We introduce signals with the instruments, the plane. So the magnetometer is at the red end of the plane, and the whole plane is magnetic, and that affects the measurement. We have to clear all of that out so we can actually find the actual signal. This plane picture's in here because I flew on it when I was at BMR. So that's the only reason that one's there. The other thing to remember is that the magnetic fields and gravity fields of a homogeneous vertical layer cake. So if you think of a cake and you have just flat layers, that field will be flat. There has to be a lateral disturbance or this change in the density or magnetization. So we come down here. So if this is flat, we can put any more layers in here that are flat with different densities, and it still doesn't affect the signal. But if we come across here, we actually get an anomaly because we've got a lateral change in the rock type. So this means we have Rainer, who worked on your project, is from Namibia. He's done a lot of work with Namibian data, so some of these examples are from him. So this is the aeromagnetics from Namibia, which is in West Africa. It's very spectacular. So from all of the mapping, the anomalies of the distribution of the magnetic minerals, you actually get to map geology. And it is, as a first pass, if you have just sand as a first pass, you're basically getting the geology and getting a big understanding of the geology. And so they have the same issue that we have in Australia, in that a whole lot of it is covered by sand. It's still...
We have a bigger problem. All of it is covered by trees.
Trees.
Yes.
Yeah.
Same thing, works just as well. And water. And also water.
Water causes some trouble.
Water causes some problems. You can't even stand on the damn stuff. So, I mean, it's the same problem. We've got undercover problems onshore with sand and regolith, and offshore you've got water, and the water gets deep.
So acquiring, like boots on the ground is something that all government groups try to avoid.
Yeah.
And so flying magnetics and gravity it sees through the trees. You can't apply seismic. You can't apply seismic with all the trees around environmentally. What's happened?
The temperature. Oh.
So the magnetic method's successful because it's fast and cheap, but also the magnetic susceptibility of minerals and rocks varies widely over orders of magnitude. So that's why it's become a very a go-to first pass method. Gravity measurements are exacting and slow. The instruments are very expensive. The other thing is the densities of rocks, there's not a great deal. It's sort of 1 to 3 or 3 and a bit, and that's what you get.
So the basalt there, Mike, you've got a 2.8 to 3, a limestone carbonate at 2.3 to 2.7.
I mean, this is everything overlaps each other, but it's not
very low range.
It's a low range, and it becomes very important is the small differences in density. So gravity measures the vertical. What we're always measuring is the vertical acceleration of gravity is meters per second squared. Except that the values that we're interested in are down in the 10 to the minus 6. So the 5th decimal place and the 6th decimal place. That's where we're measuring gravity. So the biggest change is at the Earth-air boundary. And so all gravity work needs to have terrain corrections. So in this one, the blue signal is the free air. This is from FTG. The black at the bottom here is the terrain, and the corrected data is in red. So there's significant corrections need to be applied to alleviate the terrain issue.
And Mike, just a comment, pose a question for the team. What impact does the terrain have on the strategy for using potential fields? Like, does it have a substantial impact?
No, we just deal with it. So, I mean, we take into account with the FTG, the terrain correction programs we have now is, so you need to, the one there was your survey in the Malacca Straits. It was onshore, because it was came up against the shore, we would take into account the onshore topography, then also how the topography or elevation moved into the seafloor and the water. So you take into account all masses. So the water is an issue, water depth. So, and that all gets accounted for, as does the movement of the plane. Is a very long, and to get from a measurement to an actual usable signal is a large amount of computer work and careful processing to do that. So we've got magnetics and gravity. They are related. So Poisson shows that if the magnetic and gravity signal are from the same source, they are related by a mathematical equation. So here we have this little lenticular anomaly in the gravity, which it looks as though it's a low. In the magnetics, there's some more detail in there because there's more detailed data, and it's a high. So this gives you, the question is you're asking, you know, what sort of rock types have we got that give this to us? We've got a lower density, higher magnetization. We're starting to think about rock types and lithologies just from looking at that. Magnetic gravity pulls down. It always pulls to the center of the earth because it's a monopole. Magnetic fields, the earth creates its own magnetic field, which is kinked off to the side, and so it changes with time, and that has to be affected. And so because it is not the same all around the earth, and we're dealing with little bar magnets, so when you think of magnetization of rocks, it's how well the little bar magnets in the rocks all line up. So in hematite, magnetite, there's a lot of them, and they line up quite nicely. So the shape,
when you have less ferrous material,
yep,
you ought to have
you have a lower susceptibility and lower magnetization.
But just like in seismic, right, it's about the contrast as well. So say
the contrast in seismic is acoustic and is based on the density of the rocks. Right. And so the contrast in magnetization is about how much magnetic mineral is in there, but also how it's structured. So we don't have to worry about, it's just that the Earth's surface is, because of the way the Earth's magnetic field is lined up, we don't get symmetric anomalies. They change with where you are on the Earth in terms of shape. And because it's with magnetics, you tend to always get a positive, negative pair, which in this case is sitting over the nearest point.
So it's more complicated as you move.
It's more complicated. And again, this comes to the next part, is filtering, why we do it. So if you have a vertical, this is when you have a vertical body at the pole, you get this nice anomalies. So this comes to filtering. We've got all of these effects. We've got data all piled on, sources all piled on top of each other. We've got the Earth's magnetic field we have to sort out. So why are we trying to separate and isolate anomalies from the different sources and depths? So things with different depths.
Mike, if I may stop you for a while.
Yep.
If we go back to magnetics, so in a sedimentary basin,
Yep.
I mean, especially in Malaysia, you do not have a lot of magnetic
material.
So you can't really differentiate anything except from maybe the basin outline.
I don't know. It depends on what you do to your data.
Can I just jump in there before you get into geophysics? So one of the challenges in Malaysia is how compacted the sequence is, right? It's just not, it's not just, you know, whether you've got some heavy elements within the sequence. You know, so for example, in the Malacca Straits, maybe the first 500 is reported to be under consolidated with the same velocity as water. First 500 meters. In Sarawak, same thing, right? Understanding shallow geology is really, really hard, right? And you get bacterial gas and all sorts of things. So there's a combination of, you know, you're not going to get, you in an unconsolidated sedimentary sequence, you can still pick things with high magnetic susceptibility, right? But generally speaking, under consolidated geology is very difficult in all geophysics, because as soon, you know, like if it's got a similar velocity to water, you know, it means you have to do a lot of fine tuning in your processing.
Because you are measuring from top. So what you're looking at is on the surface. So how do you?
No, we can measure. We measure for the total.
Yeah,
the total pile. The magnetics measures down to the Curie point, and so that's why there's a mixture of the highest frequency, the short wavelength ones. Yes, they come from the surface, but the magnetics has a very good penetrative power to pick up stuff well in the section.
So, you know, 15 kilometers for magnetics, for example.
I'm getting there to answering the question about
but I'll answer the question fairly for you. A different way of asking the question is, what percentage of magnetic signal is from the near surface? That's really what
none.
None. You say none?
Well, in their case, you look at the stuff. If you've got that unconsolidated sedimentary sequence, I mean, in many other cases in mineral areas, you get mining. It's from the surface. Yeah, but what we're trying to do is with the filtering is, if you look at the magnetic map and the magnetic data that you get from the Malacca survey, if you just look at that straight up as a TMI image, it's not very inspiring. But you can do stuff with it which shows that there is a lot of really good information in it,
including tectonic evolution.
And that comes into this with the filtering. It's applying a good understanding of what you can do with the filtering and with image processing. So we're going to separate and isolate the anomalies from the sources and depths and create different views, because you can see different things and highlight different features with just small changes in filters. We're trying to transform the geological signal into geological data. This is where, instead of you having to use more pictures, you actually get numbers about surfaces, depths, dips, and rock properties. And the other thing we're doing with filtering, which is something I always try to find, is finding that how far can I push the data to find every signal down to the noise level. I'm sort of bouncing around off the noise. So even sometimes you're interpreting in the noise because you can see something very fine that's important. And in terms of filtering and image processing, is a sort of a conversation between geologists and geophysicists. So it's the geologists need to help the geophysicists understand what they're trying to visualize, what they're trying to see and test. Then the geophysicist has to find a filter that helps do that and it's never one filter. There's always more than one filter and more than one image. And understand and identify the feature to be visualized. Can we see it? And then that has to go round and round a bit until you get what you want out of the data sets.
So the signal to noise discussion is a really big deal, right? So you have petroleum geophysicists that will interpret seismic, but they can't tell the difference between data and noise these days because they push the processing so hard and merge things, right? That's why having someone like Mike and Rod and others who've got the experience to see over so many projects to be able to say, well, what is data? What is noise, right? And how do we preserve the data? So most techniques in exploration You spend hundreds of millions of dollars acquiring the data, and the first thing you do is blow away 50% of the information. In seismic, you bin it, right? You probably decrease it by 30%. In potential fields, you grid it, that's 50%. So and because you're all pushed into the 3D world, you're
That's
already
worse.
moving all your information
Mhm.
and blowing it away.
Yeah. because
So
when it-
our techniques are about preserving every sample, and in seismic terms, every trace. So we respect every trace or every sample, and we preserve that in our workflow. Whereas every retail technology product on the planet will smooth it by a minimum of 30%, generally 50%, in many cases 70 to 80%. So for every $1 million you're spending, your value is only 200,000. Uh-oh. But that's critical, right? Because if you're forced into the 3D world, you need 3D products, and a line is not really a 3D product.
No, it's not.
I have
It
a
becomes.
Yep, go ahead.
Just now, I think 3 slides back or whatsoever.
3 slides back.
3 slides back.
Gravity and magnetic, where you see no, I think it's okay. The gravity and magnetic, where you see the magnetic is high, the gravity is
Oh, that
low.
one?
Yep.
Yeah, this one, yeah. So, do you have any shortcut or library saying that? So, if the magnetic is high, the gravity is low, so this is maybe correlatable to
A
I don't know.
particular rock.
Yeah.
Strange rocks.
Yeah. Do you have that? Or if the
No,
gravity is
I
high,
mean-
the magnetic is high. Sorry?
It depends on the environment you're in. Here, you'd probably have more information about it, but to me, it's an example that, low density does not mean low magnetization, that the things can be mixed up. And in offshore, where you get, it's important, I suppose, on a tectonic scale, where on the southern margins of Australia, they have there's a magnetic low gravity. Anyway, a whole lot of alteration happened with breakup, and you get a very odd either high mag, low density, or low density, high magnetics feature across the whole bight area. I can't remember what it is.
I mean, there are filters.
There are books that have all of this in it.
But Mike, like analytic signal or something like that,
Yeah.
so there are particular filters in geophysics that are better for geologists. Like because the magnetic and gravity field is a 3-dimensional field, getting the right location of the actual geology is the first step. Then you can look at the properties, but you can also run tests. So for example, in the Malacca Strait, if you said to me, the base tertiary carbonate has a high susceptibility or a low susceptibility, which one do you think's better? In our technology, it will run a million models and find the most likely, right? But what you're also asking is scenario modeling, like in basin analysis. What happens if the basement's at 7 kilometers? What happens if the basement's at 5 kilometers? What happens if the source rock is gas prone versus, you know what I mean? Like it's the same principle. It's a sort of circular process between geologists and geophysicists. Once you set up the geological framework, the geophysical framework, and the structural framework, you can then, and you have confidence about certain areas in the basin, you can start to test them. So, for example, in the Malacca Straits in the north, you've got more drill hole data, more seismic. You do a miniature case study on that versus the onshore versus the whole area. And that way you get confidence about the geology from the onshore, the area with the most data, and then the whole basin.
You need to have some sort of calibration.
Yeah, and so like it's like people talk about multi-physics and geology, but rarely do people do multi-physics with geology. They look at one type of geophysics like seismic, another type like magnetics, and another type like gravity, and then they make their manual interpretation, and then they sort of say which one's better. Where our approach is about pushing them all together So there's always improved calibration you get from more drill hole data, more outcrop, more seismic, you know. So because the potential field data is continuous, you need critical data map. Like we can make observations and interpretations throughout the whole area, but if you want to address the uncertainty, you know, like what you've done, you've acquired seismic, that will define and uplift the whole project, because you get an understanding of, you know, in the platform area, is there stuff that you can't see under that platform area? And if you use the Canning Basin as an example, there is, right? It's just that it's not easy to see. So stacking up the geophysics, it's actually a workflow issue. If you have a good workflow and it's very difficult, you'll be able to do that multi-physics approach, extracting geology from multi-physics. Sorry, no.
That's all right. So filtering with magnetics, we need to get the anomalies to sit over the top of the source bodies. So the first thing we do is reduction to the pole. This gets a bit harder at the equator. So sometimes, so this has moved the anomaly to directly over. So reduction to the pole makes it so that we move the anomalies to sit directly over the source. If it's reduction to the equator, because it's too difficult to do this at the equator, we use reduction to the equator. Now we're going to get into derivatives, which is sort of a start off for the other thing. So in derivatives, it's a rate of change of the signal in either the horizontal, vertical, or Y direction. They increase frequency content. You can have multiple orders of derivative, first, second, third, fourth, fifth, they go on. They highlight, sharpen the high frequency features. In the case of small bodies or elongated features, they sort of mark the center. So an example of this for everyday type of knowledge is driving. So driving, if we have distance, speed, distance per time is a first order derivative, and acceleration, speed change per time is a second order derivative. It's the same thing.
So Mike, why are you going to go through that?
No, I'm going to go through it.
Why do we run derivatives?
We run derivatives so that we can sharpen up the signal and get a better location of the anomaly over the source body, particularly with analytical signal. It has no analytical signal. We like to use it. It has no negative lobes, and it sits directly over the source.
So did you get that? So one of the challenges using potential field data is you have positive and negatives.
Yeah.
Removing that for a geologist is not a big deal, and it allows a geologist to think more conventionally as a geologist.
Yeah. So in this case, you get the analytical signal, you get the peak sits directly over the top of the little blue body. And if you have two of them, you get a nice little double peak. So it becomes easier to interpret. So basically, we're trying to do this is to make it easier to interpret and easier to pick bodies. So if we just go through a few of them. So this is just the RTP again. So that's the first vertical derivative in black and white. This is, I'm sorry, this is a hard rock example, but this is the analytical signal. So it's actual an anomaly, how magnetic something is sitting over the top of it. But again, you can see it's, if we go from here where it's not as, there's a lot more spread out in terms of colors and it's a wider palette. Here it's a lot more linear and you can see where the edges are.
So that's a targeting, that's the way you would target.
But where is this? I mean, in terms of depth.
Oh, this
Are we looking
surface.
at? Yeah, okay, that's the thing.
Okay, we're getting to the depth, don't you? I've got the depth covered.
Okay.
This is the tilt or phase. When you convert to analytical signal, what you're doing is you're taking our magnetic signal, you're doing some mathematics, you get two parts out, which is basically a real part and an imaginary part. So it's a bit of mathematics, jiggery and pokery. And this is the tilt derivative or the phase derivative. And I'll get back to its use soon. But again, it's highlighting like lots of the edges and bringing out the high frequency.
Mike, are you going to, because this team is really looking at both
Yeah, I know they're coming.
Drilling like the VRTP, are you going to get into?
Yeah.
Oh, cool. Oh, sorry.
Don't you worry about it.
Oh,
Okay, so this is starting to mix the analytical signal, and the total horizontal derivative picks up edges.
beautiful image.
It is pretty.
That's pretty.
That's what you've got to make. And the other thing about this is you've got to make pretty images to give to management to stick on the board room walls. That's what I always got. You had to make, when I was working for the government, you had to make an image that was useful for your geologist and an image that was really pretty that the geologist could give to the director.
No, it's serious. Like so Mike's actually an artist. Not a geophysicist or a geologist.
So here we're starting with, this is just the satellite. This is Scripps Topex SatGrav over this. I did this because I was looking at trying to get some gravity data over Sumatra because we're doing a job in Sumatra. And it happens to, because I picked a big square, that's by luck it's got yours. So this is actually quite a good image. It shows some structural features in the Malacca Strait. It's free air. Okay, free air anomalies are nice to look at, but they're difficult to interpret because you have a mixture of topography and gravity, and it's just all mixed in together. We need to get, so I just use the Scripps topo. Again, this is free data, just playing around. Oh, sorry. So that's calculating the Bouguer anomaly to cover there. So we've got RID down in the south here. We've got, because this is the seafloor basalts. But again, this is the edge of the subduction zone and into the back here. So, and then what I can do with that, you can start to see there's some actual more linear structures. It's really quite good, the satellite data. So here what I've done is
can you go back?
Like a excavation.
Yeah.
Yeah, what's that? No problem.
This bit here.
The boundary.
The boundary.
Which one? This up here or?
We are determining the
this bit in here.
No. The east-west, the transition where you were, go left, up, the green to blue boundary right on the northern coast of Sumatra. So
Up in here.
No. To the right. Right.
Yeah.
Just
there,
that one, right there.
What is that?
Is that just a color scale?
That's real.
So they're talking about east-west, not north-south.
East-west across here.
Yeah.
If you go back one slide, we can see the North Sumatra Basin over there. Yeah.
Oh, this one in here.
Yeah. Then you compare to the previous one. The
next slide.
The next slide. Yeah, that's the one.
Why?
So it is a big difference.
There's a big difference because you're taking out the sea, the depth of the water. They're taking out water depth.
So this is this.
So this is the trick. This is free air.
It's
so
water.
you've got water depth, sea, and topography all mixed in with density.
Which is,
and so you're actually not seeing it's being, the actual basin shapes are being covered or misinterpreted because of the actual, you're looking at topography as well.
Mm-hmm.
So that's I mean, it looks nice and you can look at it, but it's not the actual geology.
So what you're saying is topography, when you're looking at a map like this, the
topography is one of the biggest things.
Impact.
You can't just look at free air and go, there's geology. Because you've got two things mixed in there. You've got the seafloor topography mixed in with the actual density distribution.
Can you put the images side by side? Can you see the comparison?
Can you put those images just on the fly on one slide?
One slide.
So they can
Compare both.
Yeah, I agree.
This is yeah.
I have zero image recall, so I keep forgetting what happened.
Okay, hang on. We're going on the fly.
Or maybe actually you can put the scale, the value, so they can do the comparison more.
Yeah. It's a bit different.
But see, this is the important thing is in here, you're actually starting to see that the structure through here. So this is nice and round and looks pretty, but this is actually, you're starting to see there's actual structures coming in and through here. And if we move to this slide, so what this one is, this is what I've done is I've upward continued 25 kilometers. So I've taken the Bugay anomaly and calculated as though we measured it in an aircraft or 25 kilometers above the Earth to take it away as a background. So this is reflecting more the geology or the density distribution in the upper crust in the basin size thing. So this is more likely in the top to do with the top 10 kilometers. So in here, you can actually start to see a more structured basin that is in here rather than this is probably the boundary of the rounded thing, but of the rounded part that we were looking at before. But you actually see there's actually linear fault structures in here. And then you've got this major boundary between your Malacca Basin in here and whatever's up in there.
Mergui Ridge. Right. Mergui Ridge is further up.
Yeah. So this is, I calculate, this is a fairly standard thing that I do with satellite gravity. And this is showing the actual real structure of the geology it's taken out the deep crust and it's just got the shallower crust and the basin area in it. So this is more related to the seismic. And
so Mike, a question for you. So the Malacca Strait area response is somewhat smoother than the area to the west of it.
Yes.
Does that give inference to geology?
Yes, it does, because it's saying that there's obvious boundaries in it's difficult with a satellite. You can't get too into detail with a satellite gravity because we're relying on the gravity method, which is the sea surface topography, relies on a lot of assumptions. Getting the topography out of that uses the gravity. So we've got a bit of a circular argument in here. So you've got Scripps satellite gravity, then there's the Danish satellite gravity. Everybody that does it, you get a different type of pattern. You need to look at it at like big stuff at this sort of scale. So I would quite believe these structures that are running up through here. I believe that these things, this big ridge to change between these two areas, it's good for that sort of scale of geology.
The area to the west, though, has greater relief and more chaotic style.
Yeah, so what's there? I'm not.
So what's the difference in geology between the west and the east? Is the question. Yes, sir.
That's a very nice features there. Just at the tip of Sumatra there.
Yes.
East-west directions. The east-west direction, almost east-west direction. Not that one. Just a little bit more. Okay, that one. So that is almost the same features that you show after you filter, after you do the filtering.
Yep.
So after, basically, that is the boundary that highlighted when you do the filtering just now.
Okay, excellent. Thank you, Dr.
When you look at that, that is, I think, the younger event related to this opening of Andaman, opening of Andaman.
Yep.
And the basin, the one that you show after the filter, basically is also related to Andaman extension.
It's quite different. We just need to be careful that the satellite gravity data is consistent across the two areas.
It is, I mean, the satellite data is consistent. Offshore, it's very consistent. It all runs on the same pattern. I mean, it's just been that where there's water, you believe. Onshore, they've used the world gravity. They've taken another satellite gravity data to do the onshore stuff.
Okay.
So the onshore is less believable than the offshore. when it comes to satellite gravity, the offshore data is better.
Of course. Yes.
Except,
sure.
see, in Australia, we've published the whole continent, so it's good. But Sumatra, there's no, like, I couldn't find any ground gravity data, so that's just all satellite stuff. But in the offshore, and I mean later on when we look at the FTG data, the FTG data and this in here agree very well. So it sort of all stacks up together.
Yeah.
Sorry, if I may
Interesting. You can
send
I'm
a
coming
PDF
tomorrow to discuss about it.
600 megs. I can't download it.
No, do it. Where's the file?
Sorry.
In my what? On my desktop.
Anyway, I'll just get back into this mode. Hang on. Good. So we did that. This is like another filter which we're looking at edges.
Yeah, I can't download it. How come? It stopped at 554.
You probably ran out of this, mate. So we're 3 years on its way.
Yeah.
Do you guys want to give 5 or 10 minutes?
Yeah, have a
break?
toilet stop.
Yeah. Let's
I'll get
do
some
that.
something to drink.
Let's do that.
Cool.
They might.
Just saving this.
Can I talk to you for a while?
Should be. Oh, I should have done something before I did that. Oh, anything. We're still in the office.
No, it's connected, yes, and also I'm in VPN, but this is in your desktop, right?
Yeah.
Fine.
I should have.
Nampak patent extension of Mercury Ridge. Sampai ke Aceh dia. Boleh.
Look, how can a geologist interpret all that?
Yeah.
Look at, I mean, trying to interpret that is just chaotic.
Hey, it's not that much chaotic. It can be interpreted.
I
I
don't
can
know.
see some granite body. I can see some.
True.
Russians.
But, you know, this is one of the things, right? You do a basin study,
Yeah.
but you need to look at the geophysics bigger than the basin. You know, so it's sort of like you need to do small scale, medium size, and super large scale. And it's very, you know, like it's very difficult to do quickly. All right. Perfect. Let me just see how big this is. 18 meg, that's a bit different.
This is another good filter result of free air.
Correct. Dr. Zuha, we're having a toilet break here. I mean, some of the people are. I think you can, the same principle as the previous slide, you can really see the difference between the western area and the eastern area, but you can also see overlap, I think, in structures between the two basins.
Yeah.
Like that east-west feature you can see running all the way across between Indonesia and Malaysia. Yeah. That's 18
What is this? Are you running? You're running Wobby on this data?
Mike had made this data set for you specifically for the workshop. So Mike made this last week.
Yeah. It looks like you enhance all the lineaments or the boundary.
Yeah, so total horizontal derivative, correct. So it's basically, it's been upward continued to remove all the high frequency. And then, so you upward continue the geophysics, which basically means you're looking somewhat deeper. And then you do a derivative, so it gives you an understanding of the deeper structures rather than the shallow structures.
Yes.
So, you know, like the confidence, your understanding of the onshore Peninsular Malaysia area there, the alignment of this data set with the regional tectonics, and then the understanding of the regional tectonics in Sumatra, it's quite interesting. The Sumatra faults look a little bit more chaotic than straight lines like they're normally published, which you'd understand. that in the Malacca Strait area, you can see clear structural panels. Like, you try and break up the basin into structural styles, faults that are going in one direction. But I think ultimately the story around the traditional magnetics and gravity is that they pick up, I won't say, but there's a very clear story on tectonics with magnetics and gravity. Mike needs to present that. They both image different things. The magnetic images one type of fault, and the gravity images a different type of fault. So, Dr. Zuhar, when do you leave?
Late evening today.
Evening today. Well, I'm looking forward to seeing you. I didn't think you were coming. I'm excited.
I will be arriving around 9 o'clock.
Oh,
on the 5th.
On the plane. And then it's, just so you know, it's about 45 minutes from the airport to your hotel.
Okay.
So you won't get in, if you arrive at 9, you won't be at your hotel till approximately just after 10.
Okay.
So coffees, anyone? Yeah, Lamington. That's very Australian.
Ah.
It's coconut chocolate with jam in the middle. So that's a very Australian dessert.
So you like coconut too?
Oh, I love coconut. Yeah, coconut's wonderful. Anything sweet. Pineapple, coconut.
Except Lamingtons.
What time have we got lunch booked? Thanks. 1. Oh. So we can talk on the breaks about Sarawak and Sabah if you want. Like that discussion we were talking about carbonates in the footwall, right, in the northwest.
Yeah.
I remember mapping those carbonates as part of the regional study, and yeah, how to tell if there are interbedded volcanics with carbonates. That's going to be a little bit tricky.
I think last time before we have the mega merge to 3D the multiplier.
Yep.
Quite hard, but then nowadays is we can somehow get some features of the volcanics where you can see the cone and core and everything.
Yep. Yeah. So, because I mean, if they've been drilled right, what we can do is we can take the rock properties of what's been drilled and subtract the field from the total data set to have a look at what the impact is. Because it's a bit like seismic. When you don't understand the shallow, you can't understand the deep. So if some of those carbonates have been drilled, you can forward model so you map the geology, right? And then you forward model the rock properties in magnetics and gravity, and then subtract that from the field, and then you'll be looking underneath of it. That's the way you do it. Or catching.
Another approach, Jeff.
Yes, sir.
Another approach. Basically, we have cycle 2, cycle 1 carbonate been drilled. Then what we can do is we just measure the magnetic or ferromagnetic materials inside that, if there is any. And I'm skeptical we have high magnetic minerals inside that carbonate. So by right, if you want to differentiate between carbonate and volcanics or any other mafic minerals, it should be pretty standards for magnetics.
Correct. It's when the magnetics and volcanics are interbedded that's where it gets hard. There was a question about a statement about the footwall of Sabah and and some carbonates way out away from Malaysia and the variation between carbonates and volcanics. But you're exactly right. You can measure in the field or in the drill hole the susceptibility, and then subtract that from the total field to give an understanding of what happens below it. You know, try and
And
tune the geophysics for a particular rock type. That's the key.
that is function of inversions, where you have what do you call it, the model. At least you get some ideas about it, and then try to invert based on the data that you have.
Yeah, exactly. And so you're in essence, when you do the joint stochastic inversion, run scenario model. So you
Indeed.
change the inputs. So you map out, say, for example, the top carbonate or the top volcanic. You put the rock properties in, and then you get the software to solve for the geology around it with that assumption.
Indeed,
So you're exactly right, Dr. Suha.
That is the approach actually.
Yep.
That should be the approach.
Exactly.
But we have just now only have 3 wells that we in the area.
You only need one.
And then the features also isolated from each other, so we can really see whether it's continuous to the other area or.
And it's seismic type. There's seismic tying together. So you have to look at the seismic character, and if it's real full of gas, it's hard to see, right? And I mean, the other aspect is that the footwall in some parts of the Sabah area is so full of gas that something that should be flat is like this. And then, so what they do is they do this sort of advanced velocity analysis. But the potential field data, the traditional magnetics and gravity, for example, won't be affected by gas. But the FTG may be affected depending on the contrast.
Gravity should be affected because gas has will lower down the density of the materials.
Correct. It depends on the sample spacing. So if you have really high frequency FTG data, you will probably have some effect from the gas. But if it's long wavelength gravity data, you know, obviously it will only show big things. So, yes. But like parts of Sabah are completely saturated. Large parts are just completely saturated by the gas, and the only way you really see it is in the time seismic, because you can see the impact of the gas on the time seismic. But as far as in that footwall area away from it, the prograding carbonates, the seismic character of them, and the potential field data should give you enough information, even if they're satellites, right? But you know, it's like analog studies on character, the seismic character, the magnetic character, the gravity character of the geology of each of the areas, and because you will have 1 or 2 control points from the drill holes, and then you may have something deeper beyond the drill hole, right? As always. But then you use the character as well to help. Is it chat? Oh no, it was off, was it? I should have checked.
Which way is the on?
Red, the little red, that's on. Yeah.
On. Okay.
Warning. Uh-oh. So James, is your name up on this board? No, which board is your name on?
Yeah, one of the other ones.
He's a celebrity. Comoros. Yeah. Comoros. I know. What do you have to do to become a Commodore?
Be able to work full time for nothing for 3 years.
Work for free. Is it not working at all? You can plug it in over here. Oh, hold on, no, you can't.
There's actually a PowerPoint underneath there.
Oh, okay.
Okay.
Hello, Mike.
Hi, I'm still here.
No, I'll let you know when everyone gets back.
All right, I'll have a nap.
I'm switching from my handphone to my workstation.
Doktor tak sampai lagi, doktor. Lamanya naik MRT.
Dah sampai dah. I'm switching my handphone to my workstation. Can someone accept?
Dr. Zoha just arrived at the office. Now he would like to change from phone to workstation.
Oh yeah, we'll wait for you.
Yes.
Can you can you accept this one? Because it's still
Yes, Cedar will
Yeah,
send you.
all right.
okay. Thank you.
So what software do you use when you're in the office?
PowerPoint.
No software?
Sean use it a lot. Kita guna apa yang kami punya? Paleo scan.
Paleo scan?
Paleo
Yeah,
scan.
yeah. Okay, so really use geology.
Paleo scan.
That's good. That's good. And has Petronas got all their draw core scanned?
Petronas, yes, I.
Does Petronas have all their cores scanned?
For the core scanning.
Yeah. Is it finished?
Not yet.
Not yet.
Still ongoing.
Yeah.
The
So
core
big.
360.
Core 360, okay.
That's good. Once that's done, it's
It's
a bit
from
more
UK,
helpful.
isn't it?
I don't know. There's an Australian company called, that does it for Australia. And now I think they're working internationally, but it's all similar, right? The idea is to make it easier to see the geology from the data. And you think of all the cores they've taken and they're in the shed, but you never get to use them, So it's a pretty powerful solution.
No,
And you can,
everything went digital.
as long as the computers work, it's good.
So now they are trying to, we are doing POC,
Yep.
proof of concept for cutting digitalization.
Oh, really? Thin sections and stuff.
Sorry?
The thin sections?
No,
Or
the
rock?
cutting.
Oh, really?
So we have the core, now
Yeah.
we're going for cutting. So we try to scan the cutting and see what they can provide.
That's
you
cool.
know.
That is a good idea because it's a way of validating it. Yeah. Okay. So your databases are becoming massive.
Yeah.
Yeah. One of the things that you'll probably find with the Couchy products is it produces very large volumes of data. Has anyone tried to load the Couchy volume of data? What's the biggest data sets you normally work with in gigabytes?
Yes, you know, terabytes and terabytes.
Yeah, so I mean the Couchy product is how big?
Around one terabyte.
1 TB.
Yeah.
Yeah. So that's a lot of data. So I think to make it really usable, I think we need to carve it up, chop it up to make it a bit easier because a terabyte of points is very hard for a computer to use. A terabyte of a grid is easier. It's when you have lots, because we preserve every point, we deliver it as a point, but that's a very difficult thing for a computer to visualize.
So how do you handle the big data?
Well, we tend to, internally, we have, so for example, we can take the Couchy products and make an image of it, which you can just put it into QGIS or something like that, right? But if you're interested in a particular depth and an area, we would just trim the volume to that area. That's the simplest way of doing it. The other way you can do is grid it. So the Couchy products are generally vertical profiles. So you can convert the vertical sections from points into a vertical grid. Again, not a traditional workflow, right? How many programs do you know that do vertical gridding? It's not a common process. The key thing is to always choose your area of interest. Otherwise, you'll never be able to load your data properly. But I mean, we can produce, you want to produce in the area of interest of logic, right? So for parts of the basin in the depth centers, you probably want to load more data at depth. right? Whereas in the platform area, you're probably not as deep an area. So what you do is you just clip the data to what you want, because it's all I think we deliver as an ASCII file. So you can just write a batch file that says delete all values below with it, or or trim it to an area, like whatever the software package is that you use. Most of the time, you can trim ASCII data sets pretty simple.
Not the machine goes slow.
Well, it gives you more time to think.
Have you shared the slide, please?
Yes, I did.
Yes.
But not with you.
Oh.
With Zuhar and Sean, I did.
Because Sean still doesn't deliver to the whole group.
Okay, we can ask Sean.
Have you got a USB-C plug? For USB memory stick. It's 19 meg for PDF. Yes, yeah.
I have converted to.
Is it on? Can you get it on that computer?
Yeah, it's here.
And so,
Sean, tolong share the slide.
we've sent you the
Can you
PowerPoint.
share the PDF with everyone?
We emailed it.
I sent Noemi and Dr. Zuhar and to you.
Before we move into the next section.
Yeah.
Got it.
Got it?
17 meg.
Perfect.
And then it expands
It's
to
gonna be
1
easier.
terabyte when you open it.
It'll crash the iPad. Okay.
All right, you're good?
Yeah.
Excellent. So no one needs coffee, toilet stops. Let's kick off the next order. Wait for the boss to come.
Mike, we are ready.
You ready?
Thank you.
Image processing. This is a whole nother art form and science in itself. Okay, so we start with gridded data, they have real values, and we were trying to convert that into an image that we can view to interpret. That also means that we're pushing it down and compressing it into a color space. So that's normally they only have 250. So each color space for red, green, blues, 8 bits, 256 colors. And that's the sort of, so everything gets compressed. And that it suppresses information. Another important to think about, and it doesn't get treated enough, is the type of color lookup table you're using. Try to use linearly perceptive colors, because colors, the way we look at it and perceive things, can hide data and they can overly enhance other data. So this is part of I'm using this part of this Namibian data set because it has nice sills. So this is 300 by 300 kilometers. There's 3 generations of shallow sills in the east, which is all along here. This is a histogram of the data. So it's a histogram equalized. So we're stretching the data to fit sort of, so we have an equal distribution of colors. And this is a fairly standard color scheme that we use. Now, it's not the best color scheme because it actually it hides stuff and overemphasizes things. And really, you can't see particularly well the structure in the sills. You change it to the same image with a linear stretch and using this color scheme called Viridis, which is sort of in the open source world is around there. You get a much better, clearer picture of. So from that to this, you get a much clearer and less pointed view of the sills. So these are shallow sills, and I know the question would come up is what we can see if we have the sills are deep. So we've got this set of sills here, So the next thing I did in the next image is I calculated what the gravity field would be if we flew the magnetic field, sorry, if we flew this magnetics 3 kilometers in above where it is now. So we had the plane at 3 kilometers in the air, which is making it like we had 3 kilometers of depth underneath the survey offshore. And this is the mag with the same. So we're going from that to that. So this sort of says, okay, is there actually anything useful that we can see in this data set? And if you do the second vertical derivative, there's the sills back again. You can see them. So basically you bury those set of sills under 3 kilometers of non-magnetic sediment, and the normal TMI to the naked eye looks like it has not much in it, not much signal, but yet there they are. So that's easily mapped, still understood, can be understood that they're sills and usable. This is the important thing about aeromagnetic data. You can't just tell what you're going to get from aeromag data from looking at a TMI map. You need to do the filtering on it to actually understand what you can get. This is a zoom in on the sills area. So this is the analytical phase map. Now I've colored it. It's a phase is an angular value that runs from -90 to +90. Where it's positive, underneath the positive signal is where the source body is.
Which one is positive? Blue is positive?
No, red is positive.
Okay.
So where they got the red signal, and you can see them in the line in the dikes up through here, and in these things, where it's red, it's positive. In a phase map, the source causing the actual anomaly is under the positive phase. So this is very much like, it looks like a blue-red map on seismic, but what it gives you is a good understanding of where the actual magnetic minerals and source bodies are, because they're underneath the red.
And just to add, though, I mean, just because it's red doesn't mean the blue's not important. It's a relative color range. And also, when you start to look at depositional environments, right, you looking at those features, they look like delta lobes, right? So whereabouts in a delta lobe you're shale rich, sand rich, and then you can start to look at, thinking about understanding of the geological distribution of the depositional environment. You can then tie that to the geophysics and test. So maybe the high is in the shale rich areas, or the high is in the sand rich areas. If it's in the sand rich areas, you might be carrying heavy minerals, right? So the source has heavy minerals within the sand, but the challenge is that the composition of the sandstone may have high iron rich in one spot because it was in the inside of a meandering river compared to the outside. So that's why when you're looking at potential field geophysics, you want to have geology, you want to have seismic.
You need geology.
Yeah, and anyone, even seismic people, in my experience, when you look at potential field data with seismic, you can see geological changes in a fairly consistent. So if you have a simple continuous geological unit in a seismic facies, that on seismic looks, the character's staying the same, but the actual mineral composition is changing, and you can only see that in the potential field data. I'll show you an example of that tomorrow.
But what this is doing is it's removing the issue of where do I draw the line as a geologist on this big colored map that I've been given. So if you've got like back here, where is the line on the red? Is it on the white? Where is it?
How long would it take to interpret that, right? Probably
it'll just take forever. But so, at least here it says, okay, I now know, okay, the blue is, there's not a magnetic mineral. The magnetic minerals what's causing the anomaly is not under the blue. That's something that's different. But at least it's important, but it's saying you've got character. You've actually got a character. You've got something that looks like geology that's not overwhelming your perception of what's going on.
So it's not just doing different generations of faults, but it's giving you insight into the depositional environment. But that is dependent partly on the spacing of the lines and the scale of the depositional feature. You know,
We are still looking at surface, right?
This one is a surface one, yes. The previous one,
near surface.
I mean, near surface.
that one was calculated to be 3 kilometers down.
Mhm.
So
that one, that's 3 kilometers down. So what I'm saying is, even if you've got, sills that are volcanic sills and they're buried, the magnetics will be, if there's not a lot of intervening stuff in the upper level, if the top of it is non-magnetic, you will be able to see them and map them, depending on how rich they are.
In Australia, where the continent is 3 billion years old, right, we can see depositional environments over the last 50 million years being consistent in an area, but they move around depending on water depth.
Yeah.
So one of my past life expertise is picking paleo water depth, right, and understanding the paleogeology, which is critical. But for example, in the Malacca Straits, you might not have enough competency or in the geology. There's too much turnover in geology and it's undercompacted to get that vision, right? And it's very hard to image through the processing technique because it's the understanding of how under consolidated a lot of the geology is in Malaysia, I think is still a big learning curve, at least for outside of Petronas. I don't think many of the companies operating in Malaysia, other than probably your team, really understand that, right?
But anyway, and the other thing we do a lot of is sun angle shading, which is just to highlight directions in the data, and do that so this is the color one, this is black and white with a sun angle on it, which looks like it's coming from the northwest. And then you can lay the color over the sun angle. These are from 2 different directions. There's lots of tricks you can do, and it's a lot to do with, again, showing particular things in a conversation with the team. Just what can we, visualize? Okay, interpretation. Basics is the same. It's basically the same as geology. It's patterns, textures, shapes, data set correlations. It's all about correlating between different data sets, breaks in lines. Again, this comes down to in the modern day, because we're not working all in plan, we're working in plan and 3D, basically in 3D. So you need, some platform to integrate everything on. And it's about integrating all of these data sets together. And rock properties is a big importance. Interpretation for warning with potential fields. In inversion and forward modeling, results are non-unique. You can get many density magnetization distributions that'll fit the data. And that's the need for correlations and building of a body of evidence to produce the most likely model. An example of this, which I found when I was doing a literature search for this meeting, was Buru Oil did what we're trying to do here back in 2015 was using Falcon, which is a competitor to Bell, their gradiometry data to assist in interpretation of 2D seismic in the Canning. That was quite an interesting paper, the work. They were using it to map carbonate reefs and using the gradiometry gravity data to help identify carbonate reefs in historic seismic data.
Carbonate reefs.
Yeah. In the Canning Basin.
Canning Basin.
Carbonate buildups.
Yeah, Permian maybe. Yeah.
Yeah. Devonian.
So these are just some simple things in terms of what you can see with the mag. And you can see, I've seen this stuff in the petroleum environments is paleochannel mapping, the sills, which we've had a look at already. Kimberlites, there you go. That's if you target, if you're looking for diamonds, that's what you get to see. That's what those pimples, there you go, drill those.
They look like errors, don't they?
They look like errors, except that they're worth millions of dollars. Then you get things like, you get structures like this in the magnetics, and I'm not a good enough geologist to know what that is. It looks like flow.
Yeah, deltas.
Yep.
And then you get things like, this is from Africa, and you can get the Paleo-Okavango Delta is in the magnetics, and the delta moved to the east. So this is the old, so these things must be flow and deposits off the edge of the delta.
That's cool.
It's actually amazing. It's such a beautiful example.
So in these cases, these are probably, I mean, it's a very good example because while they're long-standing geological depositional features, they're still moving around. And so drilling the particular part of the deposition for petroleum, you know, like if you're in the wrong part of a meandering stream, you'll get shale, right? And it doesn't matter, yeah, it doesn't matter what you do. Like AVO analysis in seismic will not tell you whether it's shale or sand in the meandering river, you know, creek or river. Like you actually need to drill it and calibrate it. So, you know, things like understanding the edges of the depositional feature, you can estimate what the geology is.
But that's an amazing sort of representation of the two things. It's just really neat.
How deep is that?
How deep?
Yeah, I mean the black and white. The colored one is near surface.
Colored one is at the surface.
Yeah.
And this one is probably not, it's just below the surface. It has just moved with time.
So what you need to do is run Cauchy on that and see how stable it is at depth, because that feature will be there over millions of years.
So the delta is, so this is an internal flow into the center of Africa, southern Africa. So it means that the rivers moved. So it was coming down here, and then for some reason it went that way.
So that'll be tectonics at its best.
This is another example that we have this is TMI, where they're looking for paleo channels, which are not easily seen in this data. They have to do some more processing. So then here, the paleo channels actually end up being where you get the signal washed out. And they ended up, the reason they are important is this is onshore, is the uranium deposits. The other thing is rock properties. I know I just heard you before talking about databases, magnetic susceptibilities and density. And it's not, the importance isn't in the absolute value of the density or the absolute value of the susceptibility, it's in the difference. So the ability to know that rock A is in general like 1.1 of a gram per centimeter cubed light denser than rock B is very important in the modeling. It's those little differences. So, and I don't know if your coring stuff takes density, have densities from the drilling core or susceptibilities, but I have done before.
Susceptibility, I'm not sure.
I've done susceptibilities on core. It works on rock chip bags. That did quite a good job. We did that in the northwest shelf, just with a handheld susceptibility meter. Good job for the juniors to learn a bit of geology and geophysics, get them on the core doing some measurements, and other density scales. Just to have that, it's about the difference. When you're talking about susceptibilities in a drill hole, if you're looking for volcanics versus carbonates, again, it's not the absolute value. It's to know that the volcanics are like in the hundreds of susceptibility scale, whereas the carbonates are in the tens. And then you can put that into the modeling. having some like hard rock geology or soft rock geology data is very, very useful. And like I said, it did work with, I was just using the rock chips out of the drilling, and the susceptibility on that worked very well. And it does, then it helps with in terms of the inversion, because we can actually tie some of these things down and not allow them to be so free.
So you can restrict the range.
You can restrict the range. So all we were looking at is where we were finding that the general background rock had a susceptibility of, say, 10s, whereas the volcanic sills that we were looking at had susceptibility ranges of in the order of a couple of hundred to, maybe 500. And then we found some nice basalts in there that had order of 1,000. And so it's that order of magnitude with susceptibility. With density, it's a bit harder, but if you're allowed to get the core, put it in, get it wet, you can use density scales just to do quick measurements of density. And it does have a big effect on the veracity of the modeling.
When you say, okay, you were referring to basalt. How about in sedimentary rocks?
In sedimentary, that's what I'm saying. Sedimentary rocks, it could be just the difference between being the non-magnetic sediments have a susceptibility of like 0 or 10, and the ones that have some magnetic minerals in them maybe 100.
It's a relative thing.
The relative strength would be 100. Okay, and you're just looking to know that I've got that change, even if it's only that sort of change, that can help in the modeling.
But you've got to be careful, right? Because, if you're doing it from a drill hole, it's one pinpoint into the ground, and that may or may not be representative of that geological contrast throughout the whole depositional environment. So you do need to know, how continuous and representative that variation or that relative variation is.
And because is any of the basin come up on shore on Malaysia?
Yes.
It does. So, and is there any sort of rock outcrop you can go out and actually have a look at out there and get some susceptibility measurements and some density measurements there? Again, send some
Yeah, I know. They're going to drill it. They'll get better. I mean, typically between the onshore and offshore, there's always, not always, but generally there's a fault. There's tectonics why the offshore is the offshore. So
but it's
a good starting point.
It's a good starting point, and it puts you in the right sort of area. I mean, I think with this unconsolidated geology that we have in this basin, that we may have been overestimating the densities. The densities are probably much lower than we've been using here.
Well, when you're talking about the Paleozoic in Selat Malacca, it is hard rock. It is not unconsolidated.
Okay.
When you're talking about the tertiary cover, yes.
That's where we need the tertiary cover. I don't think you'd be looking at 2.2, 2.4 sort of densities. It's not had the chance to get turned into like rock, and you'd be looking at 2.6 for the basement.
We're looking at tombstones.
Yeah, in the base tertiary. Yeah, but Mike's talking about in the tertiary, right? So the drill holes suggest 500 meters of under-consolidated geology in one hole, right? In the Malacca Straits, you've almost got like maybe 3 or 4 different structural domains, right? Domains where the grabens are north-ish, south-ish. You've got grabens that are rotate like at a different orientation. So you're looking at in essence, a multi-basin basin. Different structural styles, different orientations that will have potentially different depositional environments. So, for example, if you run Cauchy in the south and the north, the geology that the potential field data is measuring can vary, like the actual source geology. You might have volcanics in one and ferruginous carbonates in another, right? So it's very dangerous for us to extrapolate without some type of geological input or seismic input.
but also this unconsolidated material is a very difficult, is not sort of something in Australia. We don't have it in Australia. And
only a thin cover.
And then it may be that has a density more closer to 2 than anything else, which means that if you have these much lower densities in the near surface, that'll push the basement down further because you've got less material. And so that it's important that we get some sort of idea, around how we trial some of these different density profiles across it. Even looking at seismic velocities, the seismic velocities in these different zones, to see if we can get an idea of, just on sort of rule of thumb velocity density type calculations, to get some idea about how it's changing and what order of magnitude it may be.
So traditionally, like a compaction curve, right? For shale and sandstone, I suspect in the Malacca Straits in the tertiary will be quite different to a compaction curve in other basins, right? If it's under compacted. So the challenge here, so when you're doing things like depth conversion using stacking velocities, what they do is they remove about 5 or 10% of the stacking velocities. Ironically, that 5 or 10% of the stacking velocities is actually the geology. So if you plot, when they smooth stacking velocities and you subtract 5% and you plot it, you get shales, sandstones, and carbonates. So everyone thinks about seismic as this truth, oracle perspective. But the truth is, when they process it without the characteristics of the geology. It's in a very powerful way of representing geology, but it still is smooth, right? So looking at the variation, the densities, the susceptibilities over a geological depositional feature or a particular structural style is critical, because the geology may change depending on if you've got one area with a inversion, one with extension, you'll get different rock properties. So looking at a compaction curve, and as Mike said, which is in essence the way you would depth convert seismic, which is looking at the variation in velocity, is your friend. But at the moment, you've got very limited numbers of intersections and estimates on that type. Like, how is the new seismic going to be processed? How are they going to look at that under-consolidated shallow sequence? They're going to know that it's under-consolidated, like we do, but is it really just 200 meters or is it 1.5 kilometers?
So this comes into this modeling example, which is just a generic example, is that like seismic, it's the shallow stuff, the shallow material has the most effect on the gravity signal. And so if that has radically different types of densities, then it has an effect on where the basement ends up locating. And this is
red and green line represent?
Sorry.
So what's the geology here?
Oh, this is I'm not sure where this one's, but basically from looking at it, it's a continental margin. So the red boundaries be the moho. There'll be continental margin, water depths going down, and you've got a break to the side, and you've got the necking in here. So this is just
so northwest shelf of Australia.
Northwest shelf type of thing of Australia, underplating, a bit of that. So it's a standard sort of thing. See, even here the densities are 2.2 coming into the water. So I mean, it's important that I think in this area, because of looking at the gravity data and the FTG data, that the densities are going to be quite important to working out a better concept of basement. The other one is stochastic inversion has sort of become the standard in terms of doing modeling in 3D now. And it works very well. It's the integration of many data sets, can tend to hide details a bit. We sort of get focused on everything getting sort of integrated into one thing. And again, it's non-unique as well. I can remember being to a old guy showing me once that you can put a density distribution that looks like Mickey Mouse underneath this and still get the same answer just by mucking around with the densities. So it's very non-unique. Depth estimation methods, the signal changes with depth because of the fall-offs that we have. And so as things get deeper, they'll get broader and the anomalies get smaller. And it's just what we have to do out. Now, depth estimation methods have been surpassed by Cauchy. That work has changed our way we're looking at depths now, and inversion. So the older methods tend to be inputs. So Merthian row was used as an input. So that's from 1979. Still a good method. And for a lot of, but again, it depends a lot on a guess of what the density difference is across the basement. Match filter works off the radial spectrum, and so it works on basically the gradient of these lines, given some assumptions, a fair few of them, gives you a set of depths, and so you can pick out of the data and plot areas, anomalies that come from this depth, different depths. Naudi method is good for picking dikes when you have dike structures, which you don't, and there's not a lot of that going on. Euler is very good at picking depths. The trouble is you get a huge amount of solutions, and the importance is with using Euler work, it's understanding the distribution of those solutions, and it's a lot to do with smart clustering. It's all to do with our clustering. It's without the clustering algorithms that have been implemented by Intrepid, it's a very difficult method to use. Okay, gradient data. We're getting into
Sorry,
the
Mike,
FTG.
just before you go on from that. So
Yeah.
traditionally, what methods are used for depth estimates in 2023 and 2024 in the world? Like, in the world of potential field data.
Mainly it'd be doing match filters and Murdy row. But I would suggest that the work with the Cauchy, getting depths from Cauchy will give you a better result than any of these.
Because these are very broad features.
Yes, they're very broad.
So that they're picking edges and faults, but in a very fuzzy way. So they're a good guide, but you need fidelity. You need the characteristics.
The difference with Cauchy is at every measurement point along the line, you're actually performing an experiment down in depth. So you're actually getting a far better concentration of data and a better estimate of what the depth is going to be. And you're not, it comes out as a depth, as a signal that you can use rather than another sort of pattern of signals that you've calculated, and you don't get excess stuff. It just gives you the answer, the single sort of answer that it comes up with.
And it's obviously the more data you have per square area tends to be better. So in the microstrates, the FTG data is quite sparse. So there's a lot that can happen in a kilometre, right? Some faults only last a kilometre.
Okay.
The previous slide.
Sorry, a question, Mike, previous slide.
Mm-hmm.
So it's the depth estimation method using Euler. Is it?
Correct.
So this method also will portray the measurement. I don't understand.
So sorry, what does it image?
The images of the element type.
Sorry, because in the middle picture, so we could see some element. Is it represent element?
In this case, this is just a kimberlite pipe, which is a round feature.
Okay, so with Euler, there's part of the way Euler works. It's complicated mathematics. It comes up with structural indexes. So these structural indexes comes out of the calculation, And for pipes, the structural index is about 2. So that means that you sort for any solutions out of the 78,000 that we got on this job to get rid of anything that has a structural index less than 1. So you get rid of everything that's 1, and so that's most of the data. And what you've got left is this little set here, concentrations of solutions that then, so because you get from this general mass of solutions, it comes down to sets of concentrations, small concentrations. They're your targets. And these 4 ended up being kimberlites.
So in essence, it's grouping it by style.
By shape.
Yeah, shape.
This is a very geophysics technique, because it just, without it, for a geologist, it makes it more confusing than when we started with it. It's just that you need the bit in the middle is like, you start off with this bit in the middle, don't worry about that. Here's our best guess at where to go and have a look type of thing. It's black box material.
So in this case, do you calibrate with any other data, like, I don't know, seismic
No.
whatsoever? No.
So totally independent. The same with Cauchy, completely independent. And then when you interpret them, you push them together.
Yeah.
You can interpret them individually, right? Or together. So if you want to test someone out, give them the geophysics, one type of geophysics, and another person another type of geophysics. But you know that everyone will interpret each one differently. And then if you switch it all around, so the thing is, you want to interpret geophysics in a multi-physics case with geologists and geophysicists together. But particularly with people that don't have an ego, like open-minded, it's critical. If you don't have open-minded, as a geophysicist, with my geophysicist hat on, I am happy to consider variations in the geophysics based on what the geologist gives me. But a lot of geophysicists will say, oh no, that's not possible. Right? And that's part of the challenge in doing an integrated approach.
It also comes up with when people are defending models, and I've met some geologists where they've stated that the data have ruined a perfectly good model.
Okay, sure. Mike, Sean's got a question.
Yes.
Statement.
Not a question, just
Your statement.
as a statement. So just now you mentioned that you learn what Cauchy, it can be standalone, but with uncertainties.
Yeah. If you stack up the multi-physics, your uncertainty should decrease. Right? That's good. It's a good point. I mean, I like the idea of independent validation from a technique on its own, but I would never, it's good for helping your mind think, but I don't believe people do multi-physics interpretation in the market, because there's no way of using potential field data in the retail world with seismic. It's just a line above the seismic, right? That's how magnetics and gravity is displayed, as a line.
We have a whole department dedicated to multi-physics.
Excellent.
In Petronas.
I'm sure they do really good multi-physics, but they need the Cauchy product to work with the seismic. Otherwise,
Yeah, they don't have the Cauchy product.
Yeah, so that's where, just having a line of seismic, a line of magnetics above a seismic line, sure, this goes down or this rock's different, but where exactly is it? And what is the geometry? Is it dipping, or is it, so there's a lot of value that can be attained. And I actually think that the workflow is the critical. There's the Cauchy solution, but there's actually the workflow. As a petroleum person, you like to work with vertical planes, right? Cross sections, right? Not grids. In the end, you deliver grids because you get your volumes and all that stuff. But when you're interpreting, you tend to interpret as cross sections. Yeah. So the way Bell Geospace deliver the products are grids. Right, but your mind wants to look at cross sections? So the challenge is how to superimpose the data as a geologist, right? And that's to not deliver. We're trying to get Bell to deliver Cauchy products, right, instead of delivering line data. And then you can just overlay So you have a manually drawn cross section, or you've done a paleospastic reconstruction or structural restoration. You can take that cross section and then extract the Cauchy product and overlay it, and you'll get the faults, you'll get the basement, you'll get the key petroleum system elements, assuming the geology in the area has the contrast to respond to the FTG data and the TNO. And that's one of the challenges here, where one basin may be more magnetic responding than gravity responding. So it makes it really challenging because you can make many interpretations.
But actually, I wanted to ask that how accurate is the Cauchy?
100%. What do you want me to say, Sean? I'll tell you. I can tell you 8 holes have been drilled successfully with the product in 8 weeks.
Fundamentally, that's also the point of multi-physics, isn't it?
Yeah.
Because it makes, when they're different, if they're all the same, you get more confidence. But if they're different, you have to ask yourself why.
Yeah.
Yep.
So
that's true.
And that's important in itself.
Yeah.
So what's Jeff's getting at is that if you're only looking at Cauchy, it's 100% accurate.
Yeah.
Right. But if you're looking at Cauchy and seismic,
Yep,
you're asking yourself, why are they different?
So
if they're not different, you're saying, I'm getting more confident.
So if I put my petroleum geophysics hat on, so West Patricia or Patricia and Sarawak, right? Oil, water, lots of gas, 3D seismic. So I worked on that when it was a time seismic, right? And then so we had a VSP, so we depth converted it. And the crest was okay, but everything flapped around, right? Then we had a VSP walkaway, improved it a little bit, right? Then we did a pre-stack depth migrated version, and it started to get better, but it was still moving around. Even the best data sets you can get, you've got to understand that uncertainty. And if you look at the evolution of depth conversion, it's even in an RT, a reverse time migrated seismic, it's still got a lot of variation in the depths. And so if you look at the oil water contacts between the anticlines in Sarawak, there's a fair bit of variation, because the control points really is the geology, right? The geophysics is an extrapolation, right? So what's fascinating when we apply our workflows on the potential field work in Malaysia, you get the domains, the structural domains, and you get a potential field geometry, a depth to target, a geometry and a rock property, same as you get in seismic. But again, the geology has to be responding to the particular potential field data. So if you don't have magnetic geology that responds well to magnetics, it's not going to show.
Okay.
Over to you, Mike.
Okay, so we're going to start looking at the gradient data now. And so the measured data.
Mike, you've got 10 minutes before lunch.
Yeah,
oh, sorry. We have 10 minutes before lunch.
Thank you. So we're going to look at this in terms of, we went through, we can calculate the gradients, but it's better to measure them. We get a better result, better resolution, and there's some that we don't calculate very well at all, and it's just better to measure them. So here we have the RTPs, again, this little example, and the normal gravity measurement. So if we take the first vertical derivative, and then take the horizontal derivative of it. So here is the measured FTG so we've vastly changed what we're actually getting out of the gravity in terms by measuring it. You can play all sorts of games, overlaying different things and colors, and they tend to do this a bit with the FTG data. They like playing with colors. So what I want to do is have a look at your data. So the gradient, this is the FTG data from your survey. Just it's just fairly standard, like I've just done a linear data stretch with Viridis. It doesn't look, it looks, fine. This is a great FTG, this is GZ. And here is the
sorry, does everyone know what GZ is?
It's the GZ is just the gravity measured in the vertical direction. So it's GZ. It's a funny way we've started to do this, but it's normal gravity measurements are GZ, and this is from the FTG, their measurement of GZ. That's just the standard vertical gravity in the Z direction.
So when Bell acquires data, they get a GZ, a GZZ, and a TMI.
And
right?
a whole lot of other stuff.
You get 3 core geophysics along every line, right? So normally you have one data set on one line, another data set on another, and the seismic's in this orientation and the FTG is in another orientation. That's actually one of the problems, right? That everyone's acquiring data in different orientation and that you actually can't stack your geophysics up properly.
So this is, and what we're looking at here is, I'm looking at this, joining the satellite data to the FTG data, which is one of the questions we had. So this is the free air. And basically what we're doing is we're saying that at a point of wavelengths that about, for this data, it was 50 kilometers. Okay, so there's the FTG data doesn't have any wavelengths greater than 50 kilometers. And the satellite data, anything less than 50 kilometers isn't that good, so we can get rid of it. So what we do, and this is, I just did a 50% transparency of the FTG, because the FTG is GZ is free air over the free air. They match like really well. It's a really good match. This basin area in here, these things match up. So it's actually, it's pleasing that these two types of data match well.
Yeah, so 2 independently acquired data sets.
Yeah. So what to conform the data, you take the satellite data and you do a low pass filter, which keeps the long wavelengths. The FTG data, you do a high pass wavelength to keep the short wavelengths. Then you add them together. And that's all conforming is. It's a very simple process. And this is okay, TZ is tensor Z for FTG, that's what they call it. TZ, GZ, the same thing. That's the TZ, and this is the conformed version.
Conform meaning that you have already
we've added in the long wavelengths from the satellite data. Okay, it's quite a simple process.
FTG plus satellite.
Yeah, and so you keep the short wavelengths from the FTG data. You get the long wavelengths from the satellite data, and at your crossover point, which for this job was 50 kilometers, then you just add them together.
So this is very common in potential field geophysics. I like to look at them independently and think about them independently and then add them together. Partly adding them together can give one data set an uplift, but it also can compromise a data set.
I wouldn't do this with satellite data. Basically, the satellite, you're adding satellite data, the way it's created, you get different anomalies depending on which team have done it. If you had decent ship track data or decent airborne gravity data, I'd do it, but I would not bother conforming your FTG. You're just ruining good FTG data, basically. It makes a nice picture, but other than that, it's not particularly useful.
You can see the offsets in some of those faults, whether it's left lateral or right lateral. Yeah.
So we go to the full tensor. Well, we could start this one after lunch if you like.
Yes. Yeah, let's start.
That's a good idea.
Because it gets exciting in there.
This is a bit heavier.
But so there's it's like when people do isostatic corrections on gravity. The isostatic anomaly is not a measured anomaly. It's something that is made from a model. So you're actually adding errors into you've gone to a lot of trouble to measure gravity. Then you're saying, okay, I want to do an isostatic correction, but the isostatic correction is you're using a poorly defined model to take something out of the gravity data. So it's not a particularly safe way of getting rid of long wavelength features.
So recently, a year or two ago, the Geoscience Australia's sort of guru of geophysics asked us to create a new isostatic solution for Australia, which is basically his viewpoint, his personal viewpoint over 25 years on how the isostatic adjustment should be made. And we worked with them. He worked in our office and we worked in their office, developing a modification to our workflow tuned for that company, right? So, you know, like out of the box, most technology can work for everyone, right? But one of the things I've seen over the last 20 odd years is that the same workflow doesn't apply to all geology and all terrains. And so in Malaysia, there are uniquenesses in your part of the world that in essence, the default values don't work, right? And what happens when you get young people, they'll run through accepting the defaults, right? And it can be quite dangerous, right? Because as senior technical people, you can't always get to everything and supervise the younger ones all the time. So having an understanding of what the typical ranges of particular values are within the workflows is critical, because it's dangerous because you inherit an error, and then you spend the next, depending, period of time, and then you have to go back. So why Intrepid is so successful in potential field geophysics is because there's a lot of maths behind it, and we've automated a lot of it, right? Mm-hmm. So say, for example, Mike does an isostatic adjustment on the gravity. If you have our software, Mike can send you the task file, or you the task file, and you can just look at exactly in a text file, exactly what the variables are. You can modify it, save it, and execute it, or you can run it on your version of the data and produce exactly the same thing. When you have a company like Bell or others acquiring all these different FTG surveys, how do you know that they're processed exactly the same way, right? So we have in our tech stack native FTG workflows. We developed them when the hardware was designed. Same for the competition software. So every time a data set, for example, for Australia came in, we could run the same workflow. Now, that doesn't mean the same workflow will work, because maybe it was acquired by a different group. But the point is, the learning of running that same task file on the new data set and why it doesn't work is knowledge, right? And if you don't have that strict automation in your workflows, you're in danger of manually interpreting. So in an Intrepid, we tend to not manually do anything. So even all the 3D models, right? They're all driven by a geological framework and a series of algorithms that we'll use. So we know that whatever we produce is consistent throughout the whole basin. Whereas if you gave it to me 5 years ago or 6 years ago, before I was at Intrepid, I would take the seismic interpretation, I'd fix it, I'd do a structural restoration, adjust the offsets, and then I would construct manually a three-dimensional model, one structural panel at a time, right? And during that process, I will have manually manipulated so many different aspects of the workflow that you will never be able to reproduce my work, right? The whole point about our workflows is that you can individually produce the same product. So if I die tomorrow, right, and you have my project, you can reproduce it, and you can modify it and say, okay, we have 3 generations of faulting, and this fault offset this fault, which offsets this fault. And you might say, oh, well, actually the base tertiary is conformable, right? Which it's not, and then you can change the geological rule and reproduce a new model, right? And you can test the work. The way it works in traditional petroleum exploration software is that it's all manual, which means you can't reproduce it, which means once you build a model, it's dead, right? And you start again, right? So when you have automation behind it, you can just drop the data in and it fits the rule. Now, automation is very difficult, because if you don't have enough data in a sparse area, what happens? You lose control of the model, right? So what becomes really critical is if you add a pseudo data point to control the model, you know that you need to go get some data, right? And the other aspect is, for example, in GeoModeler, you're integrating structural. So do you guys know what 3D Move is?
Yep.
So I'm an expert in 3D Move. I love that. I did my PhD on it. It's cool because it has all the structural orientation data and it constructs it with the seismic interpretation, right? So what GeoModeler does is exactly the same thing, but it also validates, you build your geological model and you validate your geology with the potential field geophysics. Where in 3D Move, you validate the structural interpretation by restoration, right? Now, restoration's good, but that's all theoretical in my head, right? But you can validate your tectonic model. So you validate that tectonic model, you build your interpretation, say, okay, that's good. Insert that into GeoModeler and validate that with you validate your geology, you couple the geophysics with the geology, you validate your geology with the continuous geophysics. So you do it with the mag, grav, and tensor gravity. So the idea is to keep pushing more data into your model to validate it. But remember this, though, if you manually build a 3D model like in Leapfrog or GoCAD, right, you can't reproduce it. Because you have a particular, you like when you draw faults, you like this orientation, this dip, because that's your personal experience because you were out in the field. Where if you look at it, you haven't been out in the field and you go, well, it's a reverse fault, so it's somewhere between 45 degrees and 60. You're at 45, you're at 60, I'm at 55. What's the answer? Well, the potential field geophysics will give you the dip of the fault. Right? So there's a challenge here where you fight between manual interpretation and automated interpretation. And you know, if I have to manually interpret one of those complex magnetic fields with all those delta planes, and I mean, I can charge you 50 grand. You know, I could work on it for 3 months, but we could also do it for 5 or 10 grand using algorithms which would apply geological and geophysical consistency across the whole data set without any personal emotional variation. And that's where you start. You start with a geological framework, a geophysical framework, and a standardized interpretation. And then you test that and develop it. So the first step is go and acquire more data. You've done that. Then do a second pass of the 3D model with all those constraints from the lessons you learn from adding more data into the 3D model. Anyway.
We are going to do that, right, Dr. Zohar? It is still online.
I think it's interesting you mentioned about the isostatic correction, because what we also in the Sabah is particularly the same thing when I want to integrate the isostatic between the CSM data. When we see that there's a deeper coordinate slab beneath the continental crust. I think that there's much more variation in terms of instead just using just the model, the Aryan plan.
Correct. So if you ran Cauchy over that same data versus, is it source body migration? Is that what you're talking about? The Bell source body, that there's quite interesting differences. One has a lot of character and one is smooth. You know, like geophysicists don't like spikes. They don't like noise, right? But I like the idea of having noise and spikes in the data because that represents what the data is. You know, geophysicists have a habit, sorry, Mike, of smoothing
you're just telling
away
lies
errors,
now.
right?
I
Smoothing
love noise.
And then you end up with, well, if this area is, this is a source here, but it's all spiky, and there's a source here that's not spiky, why? And that one might be because it's all faulted and this one's unfaulted. But what the geophysicist will do is, oh, I feel uncomfortable with all these spikes, I'll smooth them out. And then you're stuck with two things that look the same.
So,
yes, Dr. Zohar.
Those are the things that the Intrepid has been doing with the data, with our data.
Yeah, we're going to put in the geological onshore geology in it, right?
We bring in the onshore understanding to it. So now, let's say, hopefully tomorrow we can discuss again
Right.
what are the onshore understanding that we have embedded inside, because everything I think we have covered. This is more detail on the processing and how the data being processed, and when we look at this, basically this is some of it in the report. Hopefully, we can capture everything of what has been shown here in the report, because I really like this presentation. It's nice. It's short, but it covers all the essential steps inside.
Yep. Yeah, no, I agree with Dr. Zuhar. What we're really talking about here is how to understand the uncertainty in geophysics, right? How to interpret, like everyone, like as a geologist, I feel like an imposter in geophysics, right? And a geophysicist would be an imposter in geology. And so it's a classic story, right? It's about how confident are we about these products, right? And how do we test and develop them, right? So if you're doing 3D basin modeling, you want to try different things, right? But you want the most you want the most constrained state to start with. So you need a framework, and then from that framework, you collect more data, and you update that framework, and you test new theories. But we can go. As Dr. Zuhar said, we can talk through the project tomorrow when he's here.
You need to go and eat some lunch, guys.
All right, mate.
Thank you, Mike.
I'll be back. When do you finish your lunch?
Around 2.
Should we
Around
text
two.
you,
All
Mike?
right.
Yeah.
I'm going
Dr.
to
Zuhar?
go and have a Vegemite sandwich.
So now it's
Enjoy
10 KL time. So you are 2 means that 4 hours ahead.
So you're having
In
breakfast.
an hour, in 50 minutes.
In 50 minutes, we'll be back.
Only 3 hours ahead.
3 hours.
3 hours.
Yeah, 3 hours.
Okay.
It's 1 o'clock here.
Okay, 1 hour break. Okay, I will back at 10 11. Okay.
Excellent. Well, we'll message you on WhatsApp if that would help.
Okay. Thank you.
Thank you.
Excellent.
See you, guys.
So, where are we having lunch? What are you going to show me? Oh, nice.
This one we have.
I have none.
So we
I have none.
Can we
more of
lock
this.
the door?
We are getting some data.
Yep.
We just completed the survey.
Did GPX acquire data?
It's mounted in an aircraft. Oh, are we? Thank you very much. The trouble with those is because the aircraft is moving, you have to put long filters through them, about 6 kilometer long filters. And so this is showing the red signal is the raw signal out of a air gravity meter. And the bottom signal was once the raw signal's been filtered and corrected for all the plane movements.
So sorry, Mike. So what you're saying is there's a difference. Are you saying that there's a difference between the significant difference between the data collected and what's delivered?
Yes, it's you'll see. So air gravity, it doesn't get short wavelengths. It has long, because of the length of the filter that you have to put through the data to get rid of the noise. So when you measure gradients, a lot of these induced accelerations, like the aircraft bumping up and down side to side, that just gets zeroed out. And so you can capture much higher frequencies. That's why.
So within our tech stack, we can actually take raw data,
Unfiltered raw data.
straight off
And
the plane.
process it completely.
Yeah. So there's a bit to say about tensor data, and it's what is given to the market. Let's just say there's a military use for it, and then there's a commercial world use for it. We get the chance to work on both.
Okay.
Right. So there is potentially more value in the data if you go back to what is an earlier version of processing before what Bell was given to you.
So meaning to say the,
But there may be restrictions on the use of the hardware from Lockheed
Lockheed Martin.
Lockheed Martin probably has restrictions on what can be shared. It's an interesting.
So this is total field gravity. I'm not sure. This is one of Reiner's examples. I'm not sure why, but this is the money shot. So at the top corner, the top left-hand corner, the top right-hand corner. There you go. We go back. This one, you think you got basically almost north-south type of trending in there. This is the FTG. That's why you're flying it to get data that you can use. The difference is just remarkable in terms of what the different instrumentation can give you. And this is
total field gravity is satellite.
no, this isn't satellite. This is oops.
Ground gravity.
This could be airborne or shipborne.
It's the difference
But
between
the difference between those two is
the
this.
instrument.
Is the instrument.
Yeah, because when I worked for the government, all we could afford was normal total gravity, like total field gravity. So this is what we got to use. This is the gravity that I always wish I had to use.
But you know, the difference between what Mike's showing in those two grids, there's also another difference if you don't grid it.
Okay.
So that there's actually Mike's showing you one big step, but he's not showing you the best step because it's hard to see in located form because the brain doesn't handle it.
Just saying that the amount of geological information that comes from FTG is orders of magnitude more than you get from standard gravity. It's just remarkable.
Well, they call it 9 component. They'll call it
total gravity, right?
Yes.
Total gravity by FTG.
So the blurry stuff is a scalar instrument with a 6 kilometer line
filtered through it.
Through it, and the high definition is
the FTG,
showing the advantage of the noise cancellation, movement cancellation, and the non-requirement for the heavy filtering. So the difference, same platform, difference between the FTG and the scalar data.
I mean, we've got here. We're getting. It looks like the data is giving you structure in this direction, when in actual fact the FTG is showing it's in a completely 90 degrees difference. It's remarkable data to use in the petroleum environment, in the sedimentary environment.
But you're putting it into a filter. So how do you know that is real data?
This is real detail.
Yeah, but no, it's a fair question. How do you know
being filtered.
What is data?
The FTG data is not nearly as filtered as the scalar data.
No.
But eventually you're putting it into a filter, so you're molding the data.
No, this is just gridding the FTG, the TZ. So it's not actually been filtered. This one, it's been image processed, but it hasn't been filtered.
Image processed, but it has not been filtered.
No, there's no filter being applied to it. This is just the data. This is the data as delivered. The FTG TZ. I've done no extra filtering. That's just the data, the detail that comes in the data, and you can see that in your data as well.
The flight path is like this.
I don't know where the flight path on this one is. I'll show you in your data.
He's done it on.
That's probably not flight path.
Maybe that's a flight path. That's why you have that striation.
Maybe.
Maybe not. I don't think it is.
So that
because that can't be geology.
Hold on. I'll give you a case study. So if you look at the seismic fabric of any petroleum field in Sarawak in the Eastern Basin, it has a high frequency faulting fabric, wriggle shears that cross every structure. It's like this pervasive, fine cross-cutting faults across the whole area. It would look like that. I'm not saying that's the case. that looks to me a bit like acquisition, but
Exactly.
but-
Exactly.
but there's quite a lot to Intrepid's story about this, and I think Michael, you'll get into the spherical.
Yeah, I would say that the acquisition on this is north-south, basically.
Normally it's quite parallel to the survey boundaries, but it may or may not be the case. But we have tools like Trend Q that do anisotropic gridding. Like, so in geophysics, everyone's best friend is color schemes, gridding, and
Yes.
data to noise. And the challenge for FTG data is understanding the data to noise. How do you differentiate what is data and what is noise? And when you grid one component, like the one on the left, which is just gravity, and Mike will get into this, we grid with more than one component. We use a spherical gridding tool. So if you grid one
spherical gridding tool,
you'll get into it. But the concept of doing a traditional grid will highlight geology and noise, right? Then you reprocess it. But if you have a sophisticated gridding solution for multi-component geophysics, you might reprocess it 3 or 4 times and progressively get better and better and better. But you still need to be able to calibrate the truth.
You need to know how to differentiate noise from data first.
Correct. And add more data and more data, more than one component. Anyway, sorry, Mike, go ahead.
Anyway. So the direction Z, X, Y, the tensor is this 9 element tensor is a mathematical construction to handle this set of numbers. So that's the TXX, the direction. So it's the derivative, the double derivative in the X direction. Then there's cross derivatives. But the thing to realize with these is only these, it's actually 6 that are independent of each other. So you don't worry about these bottom 3 when you're measuring them. So this is the set that you measure in terms of, we get this, these ones are equal to the just flips of their friends. So this G, that one's the same as that. This is the same as that, and this is the same as that. So this is the 6 channels that come out of the FTG data. GZZ is the vertical downwards derivative. And this, so that's the actual data set that you get to measure. All of these things are like normal, a normal potential field in that they work on the Laplacian's mathematics. So instead of getting a single observation, you end up with 6 observations at the one point. It has information, it does contain information about the curvature of the gravitational field, which is how those anomalies are bending. And that geological inferences can be made from that. It allows you to grid at a smaller grid cell size to get more detail.
Which is important.
And all grids are used for interpreting. You can get a lot of pictures out of this data. And so horizontal derivatives highlight source body edges. So that's just, the top one here is TZ, and the horizontal derivative that's highlighting the edges. Tilt derivative is another thing that they use to highlight structure. The first vertical derivative is a classic, so that's TZZ, which we use a lot. That tends to be one of the ones I've been focusing on. They're just shading, which doesn't really, it's mainly just showing noise. Horizontal curvature, which is another type of curvature, marks the apex of source bodies. So down in here, we're getting the tops of these edges. The cube root of the determinant. There's a lot of these things and some are more useful than others. Now, the next trick is, because I got so many, they came up with this idea of using the RGB to join them together. So if in the red, you put the TZZ, the total horizontal derivative in the blue scale, and the total horizontal curvature in the green, you can get, it gives you this false color image. And so edges and boundaries become very highlighted in white. And this is a common method of joining the data together. It's again, it's making pictures from pictures. And
So
this
the
one,
geologist, like you guys as geologists will see things in these images that may, all like in that lower one, you might see, I'll just point, right? You might
go
see,
for it.
this could be acquisition or cross-cutting faults, but you can see the breakup of the broad panel into several events. So what Mike's saying is you use these techniques to enhance different characteristics of the geophysics so you can relate it to the geology, right? I might sit back further.
But really,
So this is
Sorry, Mike, you got a question here?
Oh, sorry.
Yeah, this one over here, really, may I know which part of the channel we are looking, where on the image is actually highlighting the channel?
So Mike, in that bottom image, which
Yeah.
channel, you've used the TZZ,
Yep.
you've run, so
The
you've
total,
you go ahead.
hang on, it's what do they use? Total horizontal derivative and the total horizontal curvature.
So those three products that are used as an input for the color blending.
I'll just go down to the Petronas data. So the TZZ has this is from this value in the red. This is in the THD is in the blue. The curvature is in green. And so when you're mixing, it's mixing red, blue, and green, and you get from that you get a color. So where you've got just green, you're dominated by the curvature signal and less so by the actual vertical or the horizontal derivative. So it starts to say when you're mapping, it gives you in some ways it's a sort of a pseudo geological map based on the tensor gravity values. So you can say that these edges where we have the blue going into the green, there'll be the same sort of edge if you've got blue going into green up in here. So this feature, this feature, and into the edges here are the same.
So you might use that for faults, for example.
I see. So interpretation wise, I mean, we usually use RGB for our spectral decomposition.
Yeah, it's the same idea.
Same idea.
Same.
Yeah. So
if you had a surface in, say, if you had 3D seismic in here, and you had a surface layer where you picked a geological surface, you could drape this over the top of it as a color layer, and then be able to relate the information from this to the seismic surface.
So for the going from Sulaiman question, so from the spectral decomposition or frequency blending, we could at least estimate the thickness, right? The frequency thickness. So in this RGB blending, so what can we expect? Only the lineament? Yeah.
So this is it's a way of
the microphone.
Maybe
I can just put it here.
Yeah, good idea.
Sorry.
Oh no, that's the remote.
Oh, it's a remote. It's not the microphone.
The microphone, I think, is in here. Sorry.
Oh, okay.
Yeah, I just realised where that was from. That's our office. Sorry.
A lot of this is to do with how to conceptually present multiple data sets together in the one image to provide information to the interpreter. And that's the trouble the problem we have with there's so much data and so many versions of the data that come out of FTG. It's a way of actually bringing it together into a usable product for the interpreter.
Yeah, so you might find that one blend is better for faults. One is better for picking lows and highs, you know, depending on the mixture. And again, this is an approach, this is about as advanced approach as you get in potential field-based work based on grids, right? And the reason this is so complicated because we keep trying to represent something on a surface, right? Whereas the Cauchy solution doesn't do that. It allows you to have a vertical difference. So you're looking at, you know, maybe 1,000 layers of this data vertically. Here, you're trying to represent the sum of all in 3 surfaces blended, or 3 images. Is that fair, John? Mike?
Yeah, and I mean, it's like, I mean, if you've seen radiometric data where we use potassium, thorium, and uranium, it's the same concept as that. And basically that gives you a pretty good geology map for a first cut. This is giving you geology. I mean, the colors mean something, the actual edges mean something. And it's a matter
what does it mean?
That's where you have to correlate it with your site, with the seismic data. It'll be different for every area that you're in because it's only responding to densities.
So Mike, so the way to interpret this is to build a structural framework first, right? So you break the basin up into a series of different zones based on the style of the faults and the geometries.
Because, okay, you say it's faults and geometries.
No,
I mean, you can see the faults.
That's the
you can
starting
see,
point.
Okay, because right now what I can see is, I mean, you can have lineaments as faults. You can have yeah, I mean, this can be faults. This can be different lithologies.
Correct.
Yeah.
Yep.
Yeah, it can be faults, different lithologies. What else can it be?
That's basically there's the faults, lithologies, and from the I'll show soon is you from the FTG data you can get a concept of mapping domes versus bowls versus synforms versus antiforms.
And like what we showed before, depositional environment, depending on the exposure.
And what I'm seeing is accumulation of depth to surface.
Yeah, it's the sum of all.
Yes, sum of all.
It is the sum of all.
There are other techniques for stretching it apart, right? So right now it's the sum of all for X and Y, you've got 3 components, but we have, depending on what the problem is, we might produce anywhere between 1 and 150 different types of products based upon what problem you've got. So there is a set of FTG-based products that we produce, some of which are not available in the market, and some that even Bell have copied off us.
No.
Right?
Okay.
So, you know, the more we share, the more everyone copies. So the key part is with a product like this is to understand the characteristics of each structural panel, right? From this representation. Sure, there's many, many versions of this. And then if you tack on the Cauchy products, you can then draw it down into the Z dimension as well. But there are techniques for breaking this up and stretching it out and looking at depth, specific depth to target and depth to geometry, which Mike mentioned earlier.
I mean, one of the ways to approach this is to start with what you're familiar with, which is the seismic data. So you have a seismic interpretation that you've done and you feel comfortable with. Then you take out the maps of the structure and of the lithologies out of that, and then do a comparison with this data to see if you've only got 2D seismic, this is going to provide a lot more information and between line correlations. And it is currently only in plan view, but that may be, if with 2D seismic, plan view is a good way to go with it, with looking at, you know, I've got a fault, I've mapped a fault that's here. Okay, this runs from here to here. I've got a change. I've mapped something through here. What's the change between this area of brownish stuff and the more predominantly, you know, blue area here? Then it's you go from what you're familiar with and then add on the new data sets and see how that expands or confirms your interpretation.
Well, the problem with slab lacquer now is because we are concentrating on the pre-tertiary.
Yep.
Yeah. So when you talk about the existing 2D, you can't see anything in the pre-tertiary.
Oh, you can see a little bit in the north, but that's it.
Yeah, that's about
Very
it.
little, yeah.
Very, very little. You can see the grabens.
Yep.
Yeah, but again, that's all tertiary.
So
tertiary
from structural theory, the young fault graben, right, will form above the older graben.
Correct.
Right. So in part, most of these grabens here may have a deeper seated basin underneath them. But when we get in, but in the Canning Basin anomaly, you have north-south, you have these the Fitzroy Trough, then you have this big Broome Arch. But the big Broome Arch isn't in fact another basin. It just comes across as an arch. So, you know, when you look at this area here, like for simplicity, this could be an arch. This is the Fitzroy Trough, right?
Mm-hmm.
This doesn't look like it has the pre-tertiary basement in it. But if you use the Canning Basin as an analog, there is in fact in the Broome Arch, which is the same equivalent to the Fitzroy, like the area south of the Fitzroy Trough, there is a salt basin in the Canning Basin, in the arch, that looks simple, right? But in fact, when you get high quality seismic, you can see there is a whole basin there that's slightly different age to the Fitzroy Trough, which would be equivalent to that. So what I'm saying is the quality of the data is really critical. And when you've got early 80s seismic or you know, let's say older seismic, unless you truly understand why it was acquired, it's dangerous to use it as a calibration point. You know, that's one of the challenges, because I mean, in this basin, you probably have kilometers of erosion in the northwest, and significantly less in the southeast. But has anyone documented the amount of missing section?
No.
So, you know, there's the vitrinite reflectance component. There's the you might find that in fact this is two separate basins with two very different tectonic histories. I don't think they'll be very different, but they will be different. And that
is something that we need to extract out from the data. I mean, as much as we can.
So sort of that band there is quite different to this in its FTG response, right? Just trying to break, that's what I was saying, breaking it down into compartments to isolate your interpretation based on a particular data set. So,
but again, what you're saying is still overprinted by the tertiary.
Correct.
So how do you take out the tertiary and the pre-tertiary remains? Then we can start talk about interpreting the pre-tertiary. We have to take out the tertiary.
So first of all, you need to make sure that you've got rock properties for the tertiary, pre-tertiary.
We don't have anything for pre-tertiary.
So then you can do synthetic rock properties.
We have outcrop data.
Yeah. So
we have outcrop data, but which
is representative.
Yeah, exactly. Well, we have a lot.
So you tend to have to do scenario modeling.
Okay.
So
and we know it's not going to be flat. It's going to be thrusted, and everything is going to be like tilted.
Complicated. Yeah.
Yeah, it's going to be complicated.
Yep, agreed. Yeah. And so if you're in deeper rocks that are harder, seismic will struggle to image something, because you're in the offshore, you're right, but you know, I'd imagine that bedding of less than 45 degrees will be imaged. Things over 45 degrees, you might not. You may not. We'll see. I mean, have you seen the new seismic? Look at this face. I can't read. Yes, yes. But you can't say anything. Yeah. So there's definitely vertical geology.
It's multi-client, but
yeah,
yes,
I know.
okay.
Yeah, just say you might.
Yeah. The
So,
new seismic is not as what I would expect.
So so what you actually probably we need to have a discussion at some stage is, so we have several basins that are stacked on top of each other, right? So several petroleum basins, right? So the Cooper Eromanga is one of them. So you've got the Eromanga, the Cooper Basin, and the Warburton Basin. Each one of those is a drastically older basin, all of which are producing hydrocarbons. So it's not unusual for older geology to be at, a different structural style, but there still will be a logical correlation between the location of these large scale faults and, if you call it, the early fault belt, right? I would love to see.
This is a starting point to come. I mean, you sit here, I've just been sitting here looking at this, and you can draw there's lots of blocks of quite big changes across it. But I mean, a lot of this FTG data, I've been looking at the papers on interpretation, and a lot of the work on it basically, you know, stopped evolving in the mid, like 2015, 16. And it goes back to, it goes back to, a lot of it goes back to careful drawing of lines and interpreting, you know, changes and differences. It's, you know, first principles type of interpretation, like down in the south here, these little pods look like green grapes. You know, what's that compared to something else? I mean, there hasn't been a lot of automated production. There's no real like production code. There's papers on how to have, guys have done some scientific inquiry and how to do some different things, but nothing is actually concrete that I've looked at so far.
We're not looking for concrete.
No, I know, but that's...
Yeah, we're not looking for concrete.
I just put this slide in so that to have a few of these acronyms sorted out. It was more, for me, I was getting confused, so I put it in there. I don't know if it's helpful or not.
It is, but Mike, as you said before, like each of those produces a product, but it depends on the actual tectonics and and the orientation.
There's at least like 12 or 13 of versions of each thing, and then it's how you choose what to use in your area is you have to go through it and see which is actually producing something that you can see. A couple of these things are rotational invariants, which they're mathematical collections of the other of the measured tensors parts. R1 can be used for looking at highlight regional density trends. Okay, so there you go. And it highlights 3D shapes of anomalous targets. The paper where I found them talking about that, the structures are extracted manually and carefully tracing the lineaments. This is going back to putting, like, it's still in the days of tracing paper. So there's a lot of data here, but I don't think, because it's not a particularly mature, it's the newest of the methodologies. Therefore, it hasn't had a chance to become fully mature in its methodology. And so we're sort of in that stage of using it as soon. So, I mean, it's still, you know, mapping and looking at correlations between the magnetics and the FTG. And again, in this one, we have volcanics, the FTG, and you can see the volcanics, but you can see the basin in here. Again, it's more about, it's not anything like super, there's no sort of way currently of processing this data in particular that will give you direct geology. We can come at it in various ways, but it still comes back to using it in inversions for looking at density inversions, and doing looking at some of the other variants of it for looking at for structure. So we're back here with this one again, to look at this, to lead into, okay, so here we're looking at the central grabens, I take it these are. So the equal mix of red, green and blue will produce white, which is, so it's just, this is very simplistic way of using the data. It's basically drawing lines and interpreting off this and comparing it with what you get in the seismic data.
But we have automated tools for interpreting this.
Yes, Dr. Zuhar, you were saying something?
Oh,
Okay,
sorry,
so
sorry.
the
That
normal,
was,
the TZ gives you improved resolution. But again, this is suffering from very standard image processing. And so this is like the array of products, but they don't tell you a great deal until you start to have a bit of a more sensible look at this stuff. So this is where I started playing around with it myself and over the last week. So this is the GZ, the TZZ, GZZ grayscale. And really there's really excellent texture and detail, and using grayscale is important. If you're looking for texture and looking for patterns in the data, it's like black and white photography. You'll get far more out of it looking at this rather than looking at colors. Especially you've got, you can start to see traces of like long linear features that are in this area in here. This is quite detailed through here. This fault, which is along here, has become important as we go through the rest of the data. So there's actually, and tighter features. I mean, if you zoomed in on this and did some other processing, we could really start, this is really thin edges. And so it does come down to a bit of like basic hard detailed mapping, treating this as a geological mapping exercise. So I had a look at the RTP. So Reiner had to process it a couple of times to get, because there was sort of questions about how good the data was. And just looking at the TMI, it's nothing to write home about. It's a bit low here. There's a bit of some highs here and in this bottom corner. But if we take the phase map of this data, and again, I put it in the red. So the red underneath the reds are over the source bodies, which show there's more magnetic material there. You're starting to see the flight line direction is this way. So we're actually getting a lot of these features, this pattern. It may be this is pushing down at the noise boundary.
It's like carbonates, doesn't it?
It looks and these nice tight patterns. It shows that even though you look at that as not inspiring, but if you do the right filtering and the right image processing, you're actually getting very good data up through here. There's a boundary across there, and it moves across into here. Now then we come to the fact, okay, we've got this. How does this correlate with the FTG? So this is GZZ. This is a hillshade from the east. So it's highlighting. I was trying to highlight this feature through here. Okay. That's what I was aiming at. It also picks up a whole lot of stuff in the north.
Yeah.
Now the important trick here is this: the red and blues is 50% transparency. So you have a magnetic body that's coming in here, truncates it up against this fault. It's stopped.
Yep.
So that's saying to me that in looking at these things and edges, other magnetic bodies are truncating against other faults. That the gravity data, the FTG, is showing you one type of thing. It's showing you structure, and the magnetic data is looking at something else in your section. But the two of them are actually working together, and you actually have in both cases good data that can be used to make, to interpret and use together. So the magnetic high in the bottom came down to this feature in here, which again is isolated. I'm not sure. I don't know what any of these things are. I'm just looking at this in terms of pattern recognition and how it ends. And as a simple test to have confidence in both the data sets. So the FTG data is good data, and the magnetic data is certainly reasonable to good. in
So
that
just
with,
to add to that, Mike, so when SETA did a 3D modeling, she found that one geophysics data defined the grabens, as in the extension direction and the faults that defined it, and the other data set defined the lateral termination points, which I think you've just shown independently the same story.
Yeah.
Right? So basically, each of the potential field data sets highlights different geological features.
Okay, again, like what I mentioned before, all these geological features are summed up.
Yeah, because we're looking at it in a single grid, but later on, when
you're going to
when
show
you do the
us-
Cauchy stuff, it's in 3D. When you do joint stochastic inversion, it's in 3D.
Okay.
So
We're going to go through that.
Sure.
Yeah. Okay. Because right now I need to understand
confidence
how to
around
use-
depth to target depth to geometry.
I need to understand the data itself. I mean, the product that you've given me. Yeah.
Yep. So you can use it.
Yeah. So that I can
100%.
use it, and then it has to be in with confidence.
Correct.
Yeah.
Correct. So we're confident that the basin geometries and the terminations of the basins and the offset in the grabens is appropriately defined by the FTG and the FTG related geophysics.
Because what you're seeing here is like two basins on top of each other.
Correct.
You've got two basins on top of.
But the question is, what percentage of the FTG and magnetic data is reflective of the
Which
the
basin?
sub one? Yeah.
The bottom basin is called Lankasuka Basin.
Okay, that's helpful. I
Yeah.
didn't know that.
Yeah, that's Lankasuka Basin. So now we are concentrating on the Lankasuka Basin.
Yeah. And how confident are you of that basin?
Confident in what sense?
What's the data that constrains it? Your understanding of that basin. Like, how do you know it exists?
It is part of the Sibumasu terrain.
Okay.
Yeah.
Fair enough.
So that's why we're going to meet with
Yeah.
later on.
Yep.
So,
So-
right now we're trying to prove up the Lankasuka Basin, and then we know that Lankasuka Basin, the extension is onshore up to the main range granite.
Yep. Okay. So you've actually got geology from the onshore that constrains the offshore, even though they may have a different slight history, they had approximately the same starting point.
Well, it has very similar history. The only reason why in the offshore it became offshore, it's because of later events.
Yeah, more recent.
Yeah, more recent event that created the tertiary basin on
100%.
top.
Yep, I understand.
But whatever that you see, for the pre-tertiary up to the onshore, from the offshore up to the onshore, it should be similar.
Yep.
But the intensity of the faulting might be slightly different, because we are
And the style.
dealing with collision between continent to continent.
Yep.
Yeah, continent to continent
Yeah.
collision.
So when it comes to trying to interpret potential field data at depth, you need to have an understanding of the structural style, because in itself you could interpret many. You can pick where the boundaries are, but if you don't understand the style of it, you could get it quite wrong. So having that insight, just the basic understanding of it being compressional, is, I mean, it's the same as the older basins within Australia as well, which a lot of basically the basement, in inverted commas, is a fold belt for Australia. The whole thing.
Same thing.
Yeah.
Same thing.
And there's up to 10 kilometers missing section.
That we don't know yet on our side. Almost 10. 10 kilometers.
We're expecting the another to be 10 kilometers right for the outcrops.
And it's pretty normal for.
Now we see the basement, the Cambrian edge. The thickness of it go around 10 kilometers.
So it's pretty typical, like whatever basin you're in, you get around 10 kilometers. So, and the trick is to look at how much missing, if you obviously fluid inclusion work, vitrinite reflectance, thermochronology work will help. Like, when was the zircon down at a high temperature? When was it reset? When was the apatite? So apatite being 120 degrees, zircon annealing temperature, I can't remember, 320 something, I don't know. Let's just say hot, right? Gas limits versus oil generation. So I think some of the the geological data more value can be. I mean, I'm not aware of what's been going on onshore or anywhere else, but you know, classic vitrinite reflectance, apatite fission track. If you've got carbonates, you can do isotope work and get if you understand the cycle of the carbonate, you can actually predict the base of the carbonate. We do that in Papua New Guinea in the Miocene Darai limestone. So we can look at the strontium isotope data and look at whereabouts in the carbonate sequence we are, because we know we have a good understanding of the thicknesses and the isotropic signature through the whole sequence. So when you start mapping out characteristics in both geophysics, geology, and geochemistry and thermochronology, that's when you start to really get your tectonic model right. But if the underlying base tertiary sequence is a fault belt, it's very difficult to interpret.
Can we show them the cross section later on?
I'd love to see it.
Yeah, the cross section. We created a cross section.
Something the blue and red color is the magnetic, right?
Negative, yes.
Correct.
Yeah, because it's interesting because we start to see the
relationships.
And the direction is actually west.
Yep.
But we know from the onshore it's actually north-south. The granite.
Yes. So the FTG data is really imaging more so the north-south, right, in this area. Sorry, Dr. Zuhad, I'm pointing to the southern graben. So the FTG data is really highlighting that north-south.
Yeah.
And you see the very south, you see the red band cutting across the end of the graben. So the actual transfer zones between the depth centers are being controlled by the magnetic signature.
Yeah.
So the question is that the younger overprinting, or is it the earlier deep-seated fold belt?
Yeah.
So if you had an understanding of the geometry of the fold belt, like as in if you could give some inclination about the pre-tertiary structural orientation.
You want it? You want to do it now, or you want to go through
this one?
I think it's up to
You can join the meeting if you like.
you can join and share at the meeting.
Yeah.
apa ni lah, kau join the meeting, lepas tu aku tunjuk terus kita punya cross section tu.
It's good seeing my emails up there. Someone's applied for leave. No leave for anyone in Intrepid. Oh, that's your leave. That's your leave.
Uh-oh.
There's no leave for you, Sita. You're off to Malaysia.
Jeff.
Yes, sir.
That's the reason why we are partnering with you on this project.
Absolutely.
Because our geology, our Paleozoic geology is very much similar to the geology of Australia, especially in the Canning Basin.
Yep.
So that's why we want to understand just want to try to understand the response of FTG in Canning Basin. If we can learn something, because what we are looking at here is to go beyond the tertiary basin.
Yep.
Beyond the tertiary basin, meaning that in most cases they refer this in Malaysia, they refer this as a basement. But
I agree.
We know that over here we have a full sequence of sedimentary rocks from Cambrian up to the Permian. And this sequence basically is similar to what you have in Canning. We have been looking at this, and probably afterwards, Akbar will share some of the cross sections that we have constructed, and using our understanding on the onshore and with some of the old seismic, old vintage of seismic.
Understand. So what happens is you've got several basins on top of each other, And what's really
Yeah.
interesting is if the early one's a fold belt, right? Before that, it was a pull apart basin. So the area started off as a basin, and then it was compressed, and then it was overprinted again. So it's very
Yeah.
complex. But if we, you know, like, it's like interpreting the Cauchy products without an understanding of structural style, you know, something that looks like a extensional feature, I can interpret many seismic lines in extension or compression with, you know, if there's no drill data. So we need that
Okay.
structural style. And you, obviously, if Petronas can share with you more about the orientation of the fold belt under the base tertiary, it's a lot easier to test and develop.
So yeah, because the old seismic basically is hardly to see anything below the surface there, below the erosion surface there, and we have to rely really on the geology, the onshore geology, as well as the geology of the conjugate basin. It's not conjugate, geology of the similar geology of other basin, and we have been looking at the on the Thailand region as well, all the way to Sumatra, and go all the way to Australia.
So
what is known as the Sibumasu history.
So Dr. Zuha, because I haven't been to the field here, I will guess that the pre-tertiary orientation of faults is probably northwest.
South. Yeah, almost not south, because it's following the regional Sibumasu tectonic.
Okay, so that aligns with the FTG faults more so, rather than the magnetic faults, which are probably imaging deeper events.
I believe so in this case, but it's just that below that tertiary, below that erosive surface, very strong erosive surface, we want to see something there. Probably Akmal.
Okay, gotcha.
Okay, let's switch to Akmal. He will show you first the geological cross-section that we have created from onshore to offshore.
Nice.
Okay.
Yep.
So this
Do you
is
want me
from,
to stop sharing?
Yes, please, Mike.
so this is from our onshore outcrops. We did a lot of, excuse me, we did a lot of field work
In Paris.
in Paris.
Perlis.
Oh, Perlis.
Perlis.
I thought it's Paris.
I know, I got Paris.
The accent, the accent.
We're just playing with you. Yes, in Perlis.
I'm happy with Paris.
It is very, very hot. It's hotter than.
Oh, okay.
Yeah.
It's equivalent to Canning Basin.
Yes, it is equivalent to Canning Basin.
The last place on it.
So we've got Akmal will go through the geology a bit. Yeah.
Okay.
We'll go through the geology a bit, and then later on we'll show you two lines from the newly acquired 2D seismic. But this is
Fast track seismic.
Fast track seismic.
Yeah, cool. That's okay.
Okay.
That's all Murphy ever drilled off, fast track.
You drill on fast track.
That's all we did. No, I don't even know if we ended up getting the final seismic. I know, nothing's changed.
Now they sold everything to HTTP.
I know.
Yeah.
I've been talking with Andrew there.
Okay, so that's line 1064. We're going to show you 1064.
What a beautiful seismic line.
And 1035. Now they are processing it. I mean, the whole thing. They're processing the whole thing now. These are the two test lines that they did for us. So I think you better start with the cross-section.
Start with the geology. That's it.
Yep, there you go. Okay, Akmal, you can go through a bit on where we are in terms of a map first.
Alright, this cross section is taken from our study area in Perlis, Kedah. Perlis.
Ada tak map
Peninsula
punya
Malaysia.
map punya location dekat mana ni? Cross section ni kat mana?
Letak dia. Letak. Ya. Okay,
We can share the screen.
Yeah.
Yeah.
We close that little thing on the side. Oh, Dr. Zuha, you're quite
Zuha.
significant now. You're the main
Pardon?
picture on the giant TV, just so you know.
Yeah, your face is like really big on the TV here.
You look beautiful. Don't worry. There's no wrinkles. No
No
wrinkles.
wrinkles.
You got less wrinkles than me.
The map. So we are looking at. It's taking some time to do it. So we are looking at a cross section from Perlis. So this is the main range granite.
Yep.
Yeah, that's the main range granite. So the cross section is going through Perlis, Langkawi. This is Langkawi.
Yeah.
Up to up. Shouldn't touch the screen.
Yeah.
So it's coming from there, Langkawi here.
Okay.
It's doing that. So we're going to see a bit on the onshore. We're going to see the main range granite. We're going to see Langkawi, and then we're going to see the offshore up to the Indonesia-Malaysia boundary.
Okay. Because I think we should have around 25 kilometers of geology.
Yeah, something like that.
And then
Okay.
Yep.
Go ahead.
a few broken images there.
Corel.
Yeah.
So show us Langkawi.
Can see my
Yes.
cursor?
Yes.
Okay.
That's
So this is the Langkawi Island where we have this peak is Mount Machinchang, followed by the tallest peak in Langkawi Island is Mount Raya, basically granite. Then moving toward onshore, we start from the Setul, the dark blue one.
Setul is carbonate,
Yes.
hard carbonate.
The age we go from sequence. Machinchang is the Cambrian Machinchang formation. So basically the thickness is around 3 kilometers.
It's west.
So
North,
okay. So the direction is from east toward
Dia macam ni.
west.
Oh.
Tak balik pun. Kita tengok dari bawah. We facing the north.
Yeah.
Okay, from the map,
That
facing the north.
pink is
From-
main range granite.
I think
Yeah, that one.
I think actually first you show an overall view first. Show the boundary, where is the Sumatra, where is the offshore, and the Langkawi, Belize, and DRZ, the Benua.
Pretty good section.
Salah.
Balik. La ilaha illallah.
Kita balik. Apa dia?
The west is on it.
Ni tak probably delay ya.
It's not that one.
Yeah. North and south. Maybe.
Sabar dengan marah sampai ni pula.
Yeah. Gotcha.
Kamu jahatnya apa?
Sebab tu dah semalam sesat. Naik tram. We were trying the tram yesterday.
Oh no.
And then because Akmal is like half in the army,
Yeah.
so he must know how to get around.
Yeah, it doesn't get lost.
He doesn't get lost, but
In the tram?
we did.
Yeah.
We did.
And they only go in one direction.
And then you always trust the ladies
Yeah.
because they know where the shops are. So we trusted the ladies. And then we were always in the right direction. So never trust people from the army. They can only navigate you when there
When
is
there's
like
trouble. When it
In the jungle.
emergencies.
In the jungle, they can navigate well.
So are you sure? Shouldn't this be
Dia dia bukan salah.
north
No, no.
and south? Because this is Malaysia and this is Indonesia.
Yes.
So we're looking west
We are looking north.
or northwest. Okay.
We are looking.
So you're looking
North.
So northeast and southwest.
Yeah.
Okay.
Is the cross section.
To the north, we have Thailand.
Correct.
Correct. Mana line dia saya boleh.
Correct. Beautiful place.
Sean buka.
So it's going to be like that.
Yeah.
Yeah.
So you say
It's going to be
east-west.
like this. Yeah, it's going to be like this. Okay, tak apa. Teruskan dengan cross section. You know where we are now. Teruskan dengan cross section.
Our cross section covered from Sumatra towards Peninsula Malaysia and part of our Langkah Suka Basin from Indonesia-Malaysia border, international border towards our mainland, which is in Peninsula Malaysia. So from our right hand side is the east and left hand side is the west. Okay. So starting on shore from Langkawi Island, we have the Paleozoic sequence from Cambrian age of Machinchang Formation, which is most likely sand dominated, and we have around 3 kilometer thickness of this Cambrian sediment, followed by
deltaic sequence.
Yes, delta.
Glacial deltaic sequence, similar to what we see in Canning.
Followed by Ordovician to Silurian Sertul group, which is the dark color, dark blue color. And we have this
mainly limestone, hard limestone gray color.
Yeah, some stromatolite inside within this group, and followed by Ordovician, Timah Tasuh, and Telaga Jatuh. We have some black shell here. Okay.
So the green is our no, the green is our
suspected to be source.
Yes, our source. We hope that is going to be our source. We're going to drill that source in 2 weeks' time.
So based on our geochemistry data, which reflect the sea carbon 30, which is from terrestrial organic source. Okay.
But it's perfect answer.
Then it's followed by the Kubang Pasu, which is from Carboniferous to Permian age, the yellow one.
So the Kubang Pasu is the sand shear plastic section that is going to be our potential reservoir.
Yep.
So it's very, very crucial that we actually map the Kubang Pasu, the yellow, very well, so that we can determine the actual structure.
So your tectonic model is the rifts form in the synclines.
The rifts forms in the synclines.
Okay. Cool.
Then after Kubang Pasu, we have Permian Chuping Formation, which is dominantly carbonates, the bright blue one. And the last one is the Semanggol Formation, the Triassic Semanggol, which is in grey color.
Okay, if you zoom out, you can see that in this section, towards the Sumatra. Okay, the yellow is your tertiary.
Yeah.
Yellow is your tertiary.
Is this 1-to-1, vertical to horizontal?
Yes.
Yes, right. This is
That
one
looks
to one.
very deep water.
No, it's not really, it's not
No.
it's not
Is there a scale in the vertical?
Vertical.
Vertical scale. So this is 50 kilometers. What's this? Because the water depth isn't 25 kilometers. Is that impacts on the style, right?
You can say that the upper crest is 35, 20 to 35.
Yeah, that's
So we're talking about that's just the upper crest.
Because you
The
gotta be
water
careful,
depth,
'cause when
water
you
depth
drop
is
this
over
to
there
1-to-1,
around
those folds are
four.
gonna be almost.
Yeah, it's gonna be
Well,
flat.
flat.
It's gonna be flat.
40 meter, water depth around the.
It's gotta be careful with that. But I like the section.
You can see,
Langkah Suka water depth is around 80 to 100.
you can see
meter.
that the tertiary is very, very thin.
Very thin.
If you compare to what you're seeing now, the tertiary is very, very thin.
And from the satellite gravity, you can see, broadly speaking, maybe the fault belt, maybe. Like it's very interpretive.
Yes, yes,
Yeah,
it is. It
From the
is.
satellite gravity.
So this is very important. All this thrust structures. So this is what we're trying to
So was
map
that,
out.
was it originally extensional in your model?
It was originally extensional,
Okay.
and then later on,
Thrusted,
when the Cebu Masu terrain collided with the Indonesia,
Yep.
with
Indochina.
Indochina,
Yeah, yeah.
then we start to have all this thrusting.
So you gotta be, if that is the case, then these faults look right in this section, right, at 45 degrees, right? So the thrust faults are only between 30 and 45 degrees. If you put this at 1-to-1, you may be too low an angle. So what you probably want to have like a steep. If you get this 1-to-1, you have the steeper faults, and then you have shortcut thrusts. So you have the extension, and then it compresses, but it compresses by 15%. But once it gets to 30, it'll break through the footwall and thrust the footwall into the hanging wall. And then, so nature always takes its shortest, the easiest path. So if it faults at 45 degrees and you're squashing it, it gets to a point where it'll say, I don't want to try and reverse up a 45-degree fault. I'm going to bust through. Yeah. So you could develop this model further to have that extensional inversion in it. But you've got to be really careful. So the thrust faults between, say, 20 and max 45-degree dips, and then extension at 45 to, say, 60 degrees. And anything steeper is a transfer fault.
That's going to be more complicated.
But that's what you do in like 2D Move or whatever, or Lithotect or whatever the other ones are called.
Well, this is a very simplistic.
Well, it's complicated. It's a very sophisticated model, but there's a lot to it.
Yeah. So now,
but the focus is from the Indonesian-Malaysian border up to Langkawi, which in terms of the structurations, we don't expect is going to be as intense as what we see onshore.
Yep.
Because as you get closer to the main range granite, so your thrust
more chaotic.
Lambda,
the
amplitude is going to be steeper.
Yeah, more compression.
Yeah, more compression.
Yeah. So you probably got 70% shortening inland, and 30 to 45%
in the offshore.
On the offshore, yep, which makes sense.
Okay, so now the next one, what we're going to show is the seismic line, the new seismic line that we shot. It is more or less where it is right now. Okay, you can show lines T4. Nampak, okay. Kita keluar itu.
Sharing one window.
You just okay. This is the new seismic. Can you zoom? So if you move towards the left, you see a thicker tertiary cover. Yeah, a thicker tertiary cover, and you move towards the right, and it becomes thinner. Okay, but please, this section, this whole section, wow. Thank you. So this whole section is only like 6 seconds, 4 seconds, 4 seconds. So we are only looking at the topmost portion of the cross section, the earlier cross section that we saw.
Yep.
Only the topmost section, not the whole thing. Remember, the whole thing is like 35. 35.
35.
Yeah.
35.
So this is just the topmost section from 4 seconds. So we will cuba tunjuk dekat carbonate tu. Okay. So these are the stuff that we noted. That looks like so it's kind of flatter on towards the east, and is as you go towards the west, it becomes we can see a lot of these triangles.
Yeah.
And these are not real signal.
Yeah.
Just pan through. Those are the grabens, the tertiary grabens. So from the fast track, we can't really get good image out of it.
And the reason for that is a good one to answer, right? So it would imply that it's a fairly monotonous sequence, maybe because like you don't to get the reflector, so you need to have a boundary, right?
Yeah, so you do not see the boundary.
So you might not see it because it's similar. It's all very similar. That would be one way. Like, like a non-answer is as good as an answer to me, right? So the takeaway from this would be that either the earlier geology is more steeply dipping, right? And the geology is either monotonous or has similar densities and rock properties to each other.
That's going to be difficult because we know that we have the hard carbonate, the division hard carbonate. We should be able to see it.
Yeah.
Because on shore, it's like you hit it with a hammer, the hammer comes back to you.
Yeah, it's dangerous.
Boing.
Yeah. So, but that would imply like it's got a low-grade metamorphic passage to it, right?
Yeah.
So if you apply that, it applies to everything.
Towards Langkawi, the island, we can see that there is more intense metamorphism as compared if you go.
It could be local too, yeah.
It could be local because we know that we have some episodes of injectites.
Yep.
Yeah.
But
I have that.
I mean, you can see, if you look at the topography of this red event, you can see all the rotated blocks, the synclines. So whenever there's an inflection, you can see the frequency of the faulting, right, in the overlying sequence. I mean, it's not unusual in a tombstone carbonate sequence to struggle to see through it. But especially if it's a thick carbonate unit, like in Sarawak, you've got tombstone carbonates in the Miocene, which are thin, so you can see through them.
But we don't expect to, if you refer back to the cross section, we don't expect to have Permian carbonate that covers everywhere.
No, I agree.
Yeah.
But if you metamorphose the sediments,
it's going to be hard.
You're going to harden everything a bit and make everything similar. Right? But but that, who's to say how local or regional that is, right? So there's one drill hole that intercepts pre-tertiary at a particular like metamorphic signature, right?
Yes, dolomite.
Dolomite. So
That's towards the border.
yeah, which is a fair way away.
Well, it's not. If you boleh move ke east dekat Singapore, Indonesia border. So
Yeah, that's a bit
the
easier.
well is around. Tak nampak dia punya apa ni? Yeah, it's somewhere there. It only touched the top part. Yeah. So we can see some complicated geology down there.
You see some gas too.
Yeah, some those gas that we were.
No, it's good to see some chimneys, you know.
At least we know there's a.
Yeah, that's what I
system,
mean.
yeah.
Like
Is it around 4 kilometers what we are seeing?
1 second.
1 second.
Yeah.
So around here, like what's the depth for this?
That's 1 second.
Yeah. So that'll be, I mean, 2 kilometers.
Yeah, that's around what? Less than that. Less than.
But there, I mean, there's some very interesting seismic features there. You've got to be very careful to not interpret some of them because they're not real events. What's a geological boundary versus what is a fault is really hard, right? in that
Right, like right now, I'm struggling to see which is signal, which is noise.
Yeah.
And I hope with the final processing, we can take out a lot of the noise. But what I'm afraid of is while you're taking out the noise, you're also taking out signal.
Yeah.
Because we don't know what's happening down here.
Yeah, so you don't know. So the way I look at it is you don't know what the maximum dip that you can image in the pre-tertiary. And I think that's the problem, right? Because if you interpret it as a fold belt, you know, in essence, you can have quite steep limbs.
Yep.
And that you'll never image, right? And what will happen with the steep overturned limbs, that'll come in as like a horizontal reflector. It won't come in as a vertical one. So
that's why we see a lot of
something
horizontal
like
towards the east.
something like this, you could end up imaging the fold, right? Or the average change across steeply dipping images, steeply dipping events. So you really, yeah, this is why you would have to be very, very careful to not interpret one line at a time, right? What you do is you insert your regional faults into this interpretation and interpret each panel at a time. Well, you do a day on each panel, and then you think, okay, how does it vary and why does it vary? And make sure that your structural style is correct. Because if you're using the onshore as an analog for the onshore, the
onshore is
the analog for the offshore, it's going to be compressional, right?
Yes, it is.
So who's to say that the offshore is 100%? Like, you know, like the amount of shortening on the onshore with the emplacement of the granites and all that sort of stuff, you could just have small inversions.
We can.
So, I mean, if it was one of the things that would answer this is when you drill a deeper hole, you do dip meter, right? Because then, as long as you can tell the difference between faults and
let's not talk about a deeper hole because
well, you're going to drill source rock, so
that is going to be onshore.
Oh,
shallow. I didn't tell you that.
Yeah,
it's around 200 meters.
Oh. You're going to do it this way?
Yeah, with an auger.
So you might, whoever you don't like, maybe me, send me out. But it's encouraging to see at least more things like the gas effects in the seismic.
Let's just imagine last time the old seismic, you can't see anything, nothing.
You know,
nothing. And then people was, I remember the previous interpretation, they put everything as red, and then put a plus on it. So it's all granite.
What other basins in Malaysia do you think this is similar to? If you had to say, in all the basins of Malaysia, where have you seen this sort of seismic response?
I've never seen it.
Canning.
No, Malaysia.
Canning is quiet.
So I did a project on picking basement, right, for Murphy in the northeastern flank of the Peninsula Malaysia Basin. And you get
Northeast flank mean that in the closer to Vietnam there.
the eastern margin of the Peninsula Malaysian.
The Malay Basin.
I might get my orientations wrong because but basically away from the eastern basin edge, and what you get is
the eastern flank
Yeah.
of the Malay Basin.
yeah.
Yeah.
You have
Closer to the Vietnam border.
correct. So we looked at all sorts of stuff to try and interpret deep, because the sequence there is too shallow to be mature.
Mm-hmm.
So we spent 6 months reinterpreting the eastern flank to try and push the interpretation deeper. And you get these smaller half grabens or grabens, but that no matter what we like, they have so Petronas has a seismic, old 70s seismic, right, called the SEAS, SEA seismic.
SEAS.
Yeah.
The seas.
Is
very long lines.
very deep.
Yes, very deep.
They were the only ones that were helpful. So is there one of those running through the Malacca Straits?
We have that much.
Because that
It is impossible for you to have a long line.
I know, straight down the middle.
There's going to be ships all over.
Oh, we got excuses, I tell you, just excuses.
We had a lot of problems.
I know
with
you
this,
would have.
with this survey.
Yeah.
But if you want to talk about the survey, you can ask Ahok. I mean, he was the one looking at the operations.
So what I would look at is look at each of those, wherever you have coherent reflectors, map the panels across all the lines initially and see if there's logical correlations. But you're exactly right. The challenge here is going to be what is geology or what is geoscience related and what is
physical crap.
Yeah. Processing artifacts or yeah.
If you go back to the east,
you can have some big fields in these strap plays.
Exactly.
Huge.
Yeah. You see, everything is like very steep dips, and as you go towards Langkawi, see all these are steep, very steep dips. I'm very sure those are signal.
But I can interpret a folded thrust structure.
Yeah, exactly. I can do this.
You've got to be confident. Well, put it this way: you would want to have someone that's seen a lot of fold belts interpret this.
Exactly.
Yeah.
Yes.
Exactly. Be fun.
Exactly. That would be fun. And then as you go towards Langkawi, towards Perlis, everything starts to get flatter after this. Yeah.
And is that because you're moving away from Sumatra that's got a regional warping towards the accretionary prism? Maybe?
Well, it's actually...
Or the other way around?
It is supposed to be the other way around. Yeah. I'm supposed to be steeper here.
See, based in the more southern part of Sumatra that I've seen seismic across the southern part, you'd have a flexure dipping down to the south. You go deeper to the south, but we're right up in the north of Sumatra, right? So we're really close to the margin of the accretionary prism. So it's not as severe here.
It should be more severe here. If you go down to 1.6 below, aku nak tunjuk carbonate tu. Do you see that? Carbonate buildup.
Yeah, there's things I could interpret there, but I'd want to know the style. Like I want to know the wavelengths, as in how broad are the carbonates that you expect?
We don't know. I mean, I'm looking at this first pass and said, damn, that looks like a carbonate buildup. But you know, it's if you look at the onshore geology, that's impossible. You can't have things like that if you compare to the onshore geology. So now, but my problem is, so which one is correct? I mean,
so one of the techniques you could use is wipe out all events dipping steeply this way across the whole seismic. And what does it look like? Then wipe out all events dipping this way.
Okay.
Like, you know what, like a magical, like one of the things when I was teaching seismic processing, what we do is like we almost erase. You get rid of, so you get an eraser digitally and wipe out events that were, because when you start looking at these things, you go, okay, this is really strong. This is really strong. Migration style, right?
Migration style.
So the overprint of what you're hiding there in the geology. So if you remove this trend, but leave the intensity and the amplitudes there,
what do you see?
What do you see? I mean, this seismic's really good compared to things like onshore fault belts. So like, I know it seems complicated, but as far as onshore fault belts go and seismic, at least you've got something continuous and coherent. I mean, when you've got a strong carbonate unit, so to give you a bit of for a case study, in New Guinea where they have a miocene carbonate that's about 1,200 meters thick and it's ferruginous. Ferruginous
Wow.
at surface, you know, high velocity data, right?
Yeah, obviously.
You know, the critical thing why they couldn't see this, besides the geology is quite steep in the forelimb, and I can show you an example tomorrow. One of the, first of all, understanding the thickness of the carbonate and the sequences. Once you understand that, you're halfway there. The single thing, there's always something that hinders us to see deeper, and maybe velocity analysis or, you know, reanalysis of the core, looking at the densities might help. But believe it or not, in Papua New Guinea, the most critical bit of information that stopped people from seeing deeper was understanding the water table.
Oh.
And when they understood the shallow water table inside the carbonates, they could then see below it. So there are things that can
filter it out.
Well, you have to reprocess in that case.
Okay.
But use sort of tomography and stuff like that. But
we're going to show you the next line.
Okay.
This is going to be a strike line.
I like strike lines.
Yeah.
I like strike lines.
I don't like strike.
No, I do. It's a bit that no one likes looking at.
Yeah.
I do. I'll tell you what. You can see all the faults, the compartmentalizing faults.
That's Dr. Zuar again. Okay. Right. So this is a strike line that goes, can you show the map again?
Almost north-south. Northwest, southeast direction.
Lepas tadi ada. Okay. Atom.
So experimenting with the velocities at that base tertiary zone, I think, is critical.
Tak apalah, tak apa. Coba share screen to the slide.
There it is. So we're going to look at line 1035.
Okay.
Yeah? 1035.
So
okay, that's line 1035. This is strike. Can you zoom in? You start from the north dekat kanan, sebelah kanan. Yep. So, yep, there you go. So again, it's around 4 seconds. Again, the top part of that huge cross section that you saw. Yeah, this is just the top part. So you can see the tertiary cover.
Yep.
That's taking a lot of the signal. Now you can see all these triangles.
There's a few multiples in this.
You see a lot of those triangles.
Yeah.
Are those signal? Are those artifacts?
I mean, this one. You know, like the question would be this event here. looks like they've applied a filter to remove the multiple on that one. But like that one, 1.4, is though it's that batch there.
Yeah, most probably that's another.
But I'd be a bit careful about the processing in the sense that if that is a multiple, you see how that's bland? That they've removed the multiple at the cost of the geology, maybe.
Yeah.
That's a common practice where, and that's the critical depth that you need signal in. So just for your benefit, Dr. Zuha, I'm saying the little
You can't see your hand.
I know. So the little
I can't see.
I know the little rift in the far right where the mouse is there. So that's a
Far right.
at one point, I don't know. So you double that down, you can see the anomaly down here. So that's a multiple. But if you take the base tertiary, the horizontal event, which is at about 0.75, and then go down 7, you see that band of really washed out seismic. To me, that looks like the process CGG's removed the multiple, but may or may not have left the geology.
Yeah, basically try to push very hard to remove that strong event.
Yeah.
Most of the horizontal events, blur horizontal basically is artifact of filtering multiples.
Yeah.
You can but again, the one that Zul mentioned, the triangular shape, that one, the wedge shape, that one is, if we look from the gravity point of view, I'm sure that this line will cut a small graben, graben, which align either in the north, will cut the part of the graben, not really the east-west direction graben, because most of the graben basically is also following the directions, but I think this line is cutting some of it at the oblique angles. But the graben is small.
Yeah.
But we are not interested at that graben because we know already that is the tertiary graben. What we really want to understand is the deeper, more than 1 second. 1 second and below.
So you could interpret this as mostly extensional, the deeper sequence. You could, and you can interpret it as compressional as well. And to be frank, you can't tell the difference without having some geology. But
that is another reason. That is another reason to overlay the WOMI, the fault detections from the magnetic and from the FTG.
Yeah, so I would overlay the Werni products and the Cauchy products on this, and to look at the coincidences of sources.
That's why we need your help to help us interpret this.
When are you going to finish processing it?
No, we're gonna have our
like final stack.
Final stack is going to be July, but by May, June, we're going to get something. We're going to get the almost final product. They're going to do like 4 iterations. The second iteration is going to be in May.
So you want to have actually an interpretation in May to feed into the processing workflow.
Not really. I think the processing workflow is like locked now.
Is it?
So they're just
CGG is tough to contract.
Yeah. So they're just going to go through the production now.
Yep.
Unlike us.
Time is flexible in Australia.
Yeah, I can see people running around on a Monday. You don't see that in KL.
People don't work in this area. Yeah, only us. Everyone else is on permanent holiday.
I think so.
Oh, yeah, I mean, like
very wealthy area.
To give you an opinion, like what you want to do is look at a couple of lines parallel to each other. I know we're looking at crisscrossing, and I'm happy to see this. This is good, but to look at the structural coherency and the geological consistency of it, you really want to actually just lock into one of the best areas you've got and try and develop different models in that area before extending over a big basin. Because like when you're trying to interpret a basin scale project, you have to understand the structural style. And if there's more than one structural style, that's fine. So you need to interpret it twice. Right? And sure, you can rotate faults a little bit, right? But it's, you know, like if I interpreted that as a pure rotated extension with just a whole series of geological units stacked like bookshelves, because it's been compressed twice as well, it's been compressed by 70%. I get it, right? You're going to be in what looks like extensional, but it's going to be a fold belt. So, but you're not going to have traditional traps, so right? If it's a set of bookshelves. So, you know, I'll just put my positive hat on and say that just below the base tertiary is the world's largest discovery.
That is the thing that we're trying to preach as MPM.
I know.
That's
well, I'm good at helping investment, and I'm very good at getting people to spend money. Yeah. So, you know, like without understanding, you'd have to apply a set of case studies like what you're talking about. But the Fitzroy Trough isn't quite fold beltish enough.
Yeah. The Canning Basin for us, it's more on the lithology, the deposition,
and the thicknesses. Because I think the thickness, like, I'm not sure what you're thinking back to your cross section before. You know, like there's plenty of documentation on the Canning Basin thicknesses of each of the units.
Exactly.
So you can have like a P10, P50, P90 geological thickness.
Yeah.
So minimum, which, you know, the thickness will give you it depends. Like at these depths, it'll switch between gas and oil window, right? And if you pick the thickest unit, you'll be well into the gas window.
We are hoping to get gas.
So has anyone, I guess you can't do any sniffer or airborne laser fluorescence in this area because of the number of boats. That's really annoying.
There's no point. We tried.
Yeah.
We tried that. There's no point.
So with the onshore geology, maximum depth of burial and the timing of it, you can get commercial samples.
We have.
Okay.
We have outcrop samples. We've gone through the lab analysis of the source rock.
So if you've done apatite zircon, apatite, because if you do apatite fission track analysis, you'll get when did it hit 120?
Yeah.
And if you know it hit 120, you know it was buried in essence 3 kilometers, which is deeper than what that is.
Right? Dr. Zohar, so can we do it? Enough money, right?
Fission track analysis. Fission track analysis.
At least 1 sample, 2 sample.
I need to check.
China. China is always cheaper.
I need to check the lab.
Yeah, send it to China.
I mean, vitrinite reflectance will give you thermal maturity. But,
yes.
But if it's
we're done.
Can't do it.
We have done the VR. We have done the VR.
And what was
then
that
we're
number?
going to.
What was the number for VR?
Of course, it's going to be
4.8. 4.8.
Dead carbon.
Okay. Yep.
But dead carbon is now.
Yeah.
Now. So we managed to restore it.
Okay.
To its original condition. What was it? Yang dah restore. The VR yang restore tu berapa?
The restore is positive. It's good. It's good number. It's all in the gas window.
Here on my iPad. I can't remember.
Yang
dah restore.
Tazilan
punya slide yang dia kata dia dah restore. Don't get it.
That does. I mean,
yeah.
As long as you've done it, that's fine.
We've done that.
Yep. So, I mean, I think when interpreting this, you probably need to look at it as build a couple of Rosetta lines, but you interpret those two lines using all data, right? You don't just look at two seismic lines and say these are the two best lines. What you want to do is take the best two lines and take the structural and take the information from all adjacent lines and try and you really need to interpret, say, 5 lines in a row, and then build a Rosetta line in the middle of it.
Before I do that, I would need magnetic and FTG to tell me what are my boundaries, my major faults, major lineament, so that I can use that as a basis.
Yep. No, we can do. I can show you an example tomorrow.
But take out the tertiary cover.
Yeah, or you can just. I mean, in my past life, I would just I'd actually just delete everything above the tertiary in the seg Y, so no one would even look at it, right? And just get them to focus, because you can. I don't think CGG can do it, but we've got some examples of Cauchy and overlaying that on seismic, and you can see that we picked a fault, and it independently of Cauchy, and it matches.
Yeah.
But in Cauchy, you can also see the same feature again repeated, but we haven't picked it. Right? We don't have the seismic. We don't, and it's not obvious in the grid, but it looks like there's a set of faults. So in essence, the interpretation is sort of like evolutionary. You do the first framework pass, then you introduce new data, and then you integrate it properly. Because I mean, normally the first framework, geological, geophysical framework, defines the foundations for a more detailed.
Correct.
So you normally pick a smaller area and infill you've infilled the whole basin. So in essence, you can't. I mean, you can choose part of it, but there's no way the boss is going to be happy with just interpreting part of it.
No. Now we're going to interpret the small.
The 1/10 of the data after spending.
So what happened to the rest?
Well, we chose the best area, but normally you develop with the cluster of where all your information is best, the highest resolution of all your data, and then you build out.
All the wells only penetrated the tertiary. Only 1 or 2 wells.
Well, the one in the south got to that in the rift.
Dolomite.
Yeah.
Okay.
Well, this is complicated.
It is. Yeah. It is. That's why we need your help.
Yeah. No, that's cool, because I've seen this before. This degree of, I've seen a lot worse than this, like literally.
Oh, really?
So you just basically build it on structural theory. So, like things like, what is the frequency of folding?
Yes.
Exactly. Things like that. And so
that's what we're trying to do with the cross section.
So with the onshore, is there 30% more shortening than the offshore?
Yes.
So if you have so literally you interpret the onshore and then you deconstruct it by 30%, literally copy it and paste it in there, and go, okay, what do we think?
I'm supposed to have the limb here and here.
Yeah.
I'm supposed to have the fault here. Yeah. That's what we're trying to do.
Yeah.
Yes.
What do you think about taking the information from the onshore?
Yep.
The outcrop and everything, and forward model that.
Yep. As a minimum case.
Yeah.
Yes.
And compared to what we see here.
Yep. So it makes a lot of sense. So normally, if you're on if you treat this like an extensional basin, right? Normally the sedimentary sequences on the highs, which are normally the onshore, are thinner, right? So if you take the thicknesses from the onshore and apply them in the offshore, that would be the minimum thickness. Now, there's a couple of assumptions. If the onshore geology, if the structural style means that the geology is boudinaging and thinning, right? If it's actually thinning, you'll underestimate it quite significantly. So you do have to know in the onshore, if a particular unit is present in a fold, right? It is whether it's its true thickness or whether it's thickened or thinned based on whether it's in the hinge or the limb of the fold.
What about seismic forward modeling? I mean, taking.
Yeah, so we can take GeoModeler, we can forward model a line into seismic. We can forward model it into potential field, like whether it's magnetics or gravity. So the idea, I think the next stage is probably really a collaborative approach with geologists and geophysicists from all groups working together, right, and testing scenarios, right? So no one, I mean, Dr. Zuhar knows it. He probably knows. I mean, he's been doing all the onshore, so he knows all the onshore and offshore information. But we need to set some structural styles up. So if you took, for example, like your interpretation of the onshore is concentric constant thickness modeling, which is fine. It's a perfect way to start. Right?
That is starting point.
Yeah. So generally speaking, they're constant thickness.
Yep.
And the offsets are, I was sort of thinking that the offsets would be, and it's a bit variable, but I was thinking that the compressional offset should grow towards the right of the screen. Generally speaking, they do, right? Except for the one in the far left. Right, and there's a granite or something there. So, you know, is the structural style constant thickness in the onshore? That's a question.
In the onshore, yes.
So you don't get significant thickness variation.
No, we do not get significant thickness variation.
So that's
we're going to verify that with the 2 boreholes that we're going to drill.
Okay. Because if it's constant thickness, it means that the geology was quite competent when it was deformed.
That's why we need to look at Canning. Do they have similar?
We don't know
because
the thickness, right? Onshore.
sorry,
We know the thickness.
yeah, from our mapping.
True thickness?
Yeah, yeah. We have the thickness. That is true thickness.
Yeah, I know, but we don't know the vertical scale.
No, we don't know the vertical scale.
Top secret.
What was it?
8 kilometers.
8 kilometers.
That's about right.
Yeah.
So I'll show you tomorrow an example from Sarawak where I took the offshore Sarawak, which was covered in 3D, and forwarded modeled it into the transition zone and onshore Sarawak, because all the 70 seismic in the transition zone and on the onshore is terrible compared to the offshore. So the idea would be to take the onshore, so you restore the onshore, then forward model it into the offshore structurally, right? And then that interpretation would then be you'd use the potential field data to validate it. The sum of all rock properties below every X and Y point equals this magnetics, this gravity, this FTG. So while you can have, like in geology, you can have an endless number of interpretations. While Mike says that there's no one unique solution in potential field geophysics, it will certainly destroy a lot of the interpretation, right? And I think that because there's probably limbs, and if it is truly compressional, you know, I'd be given the base tertiary acoustic impedance difference, I don't think you'll image anything over 30 degrees in depth, like a 30-degree depth.
Yeah.
And that's really important, because while you may have amplitudes or reflectors that are steeper, understanding theoretically what the maximum dip of a depth seismic line, like of it, if you know that generally speaking you cannot theoretically image something steeper than 30 degrees because of that big unconformity, then you can say, okay, I can look at the deeper sequence. There's multiples. Okay, I can deal with that. I can check, right? Systematically. I can look at the structural style. I can validate the interpretation by forward modeling the onshore to the offshore, and then forward modeling that to look at how the potential field responds. I mean, ultimately, you'll probably need to get this reprocessed once you have a really good understanding of the velocities, and I know that's hard because CGG is so expensive, I would probably get, if it was me, I would put it out to say 5 companies, 2 lines, and say, whoever processes the best line will get another contract. Right? No, I have a license of Promax, but there's only so many things I can bring back to life from my past. But you know, the opportunity here is a proper integration of multi-geoscience disciplines, right? You're going to have to do it, and you're going to have to, and I'm sure Dr. Zuhar agrees, you have to have a set of possible styles of interpretation, you know, shallow thrust versus steep thrusts, and how does it fit across, you know, a group of seismic lines. Then you develop and test the model, and so you can say for everything in the base tertiary, it's allowed to move plus or minus 10%, right? The actual formation boundaries, or you can change the rock properties. Which are the most sensitive? Probably the rock properties, I think. Because if you've got dolomite, you're not sitting with primary geology, right?
Because
you have fractured basement.
We have a strong hold on what the ethology expected. The only problem for us is the structure.
But what about the density? Because I mean, even in the shallow sequence, you've got velocities of water at 500 meters in the ground. You know, and if you don't get those right, how do you see below that? And then you've got that complex base tertiary. It's clearly like it's, if you go back to the seismic, you look where all the signals being collected. So to me, that hints that they haven't got the right velocities. Because like, I'm just picking, maybe for the math. I mean, there's a substantial amount of signal in here. I mean, here, there's not a substantial amount of signal, and you get something underneath of it. You might have to do some type of seismic topography or preset depth migration on that shallow sequence.
Expensive.
I know. That's why you do a test line.
Can you guys do it?
I'll never say no to anything. You have to talk to Dr. Zuhar.
Yeah.
Tomorrow we talk.
Yeah, tomorrow and
Let's talk tomorrow.
Shall we let Mike continue the?
Yeah, I think Mike has a few more slides.
He's got about 99 for you.
I've got his slides.
Let's let Mike finish off the
Yeah, I hope we can.
Because we need to go by 5.
Yeah. I warned you that I talk too much.
He
Mate,
does.
I mean, I was going to come to Malaysia, but there were tenders open and I couldn't talk to anyone. So I deferred coming in.
Okay, Mike.
Okay.
Be quiet.
Go forwards, Mike. Oh, okay. These are phase maps of the FTG data done in the same way. So the red is over the source, the higher density, and blue is over the lower density. So it's just that's for the TZ, and that's for the TZZ. So again, I'm probably pushing down. This is probably out the noise barrier, but I think depending on what we're looking at, it does have interpretable signal in it. Now I talk about the data-driven interpretation, which is sort of based on WRM-E. So the horizontal derivatives highlight the source body edges. So they pick the edges of the bodies in the from the signal, and from that we can calculate the 3D cloud of edge points.
So that's all automated, right?
That's automated.
There's a few variables that you set when you run it, but that's automated.
Now, this is just some old work I did, which is the yellow here. This is aeromagnetics off the coast of coastal Tasmania. And this was petroleum. We were looking at the petroleum basins offshore. Just to show that when we're talking about this and the source, the phase mapping geology. So this is the geology map, and these very thin lenticular things are following along the geology and mapping geology better than the geology. This is all bush country down. It's like your stuff covered in jungle and horrible and messy. But it actually does work. And when you get out get into things where you've got fatter, larger things, this probably means that there's faults running down through here, that there's a major drop off into this area. And we can combine these. This is in Sumatra. It's a small gold prospecting area that we were doing a job for. So this is joining these products together. So we can calculate the worm-E solutions. And from the worm-E solutions, we can then derive surfaces in 3D and dip solutions for those surfaces. So they're contacts. We don't know whether they're a fault or what they are. It's just it's a density contrast across which we can calculate there's an edge there. Then you can add in the source bodies, and you can see that the edges, the contacts that we've come up with and the dips on the contacts match the edges of the source bodies. And on these source bodies, you can then, so we've basically taken away the geophysical signal and come up with a set of geological parameters. So we've got surfaces, dips, locations of source bodies, and from these we can calculate the depths of these on these source body things. Now, currently this can be done on really small areas because the contacts and dips and depths are still a manual procedure. We haven't automated that yet, but it shows an idea of where we're trying to go with this, actually getting geological content out of the geophysics that's directly that you can input into your interpretation systems. While I was looking for what was happening with interpretation and products that you could use for FTG data, I came across this is from 2013, that we can actually, so this is looking at curvature, which is KM is the mean curvature, KG is a Gaussian curvature. It's a different way of looking at curvature. And by doing the ratios between these in this matrix here, you can come up with domes, antiforms, saddle ridges, synform valleys, and bowls, and then that comes up as a map that you can use. So again, getting away from FTG signal, GZs, Zs, and all this stuff, and actually coming to something that actually maps a geological structural styles that can be used to interpretation. Now, I haven't seen this. Doesn't seem to be anywhere. It seemed to come up in 2013, and nobody's put it into production that I can see. But I think it's actually quite an interesting idea. It's not hard to implement, and I thought it might be of some interest to you guys is trying to find new ways of actually getting value out of the FTG data.
So what Mike's saying, he's suggesting to James that he gets his development team and make some small changes to our code to try and produce that.
So what we've been doing is looking at other ways of what, as a result of this project, we've been thinking about that we're deficient in products that actually give you a geological view of things. But that's also the story with the acquisition companies like Bell. So we think there's a bit of a general problem. So we've had Rainer look at it, and we've had Rod look at it, and now we've asked Mike to look at it. we're thinking that there are some additional products that we could get our development with just up in the Brighton office to fairly easily develop out of this. With a view of creating more geology-friendly product, more geologist-friendly products. Because
I mean, is this something that would it'd be useful to you? I mean, I'm just working on what I can get to a geological parameter out of the geophysics in an automated way. Well, everybody's quiet.
Thank you, Mike.
So yeah, it's this, and this is like FTG is not so. I've just approached it as a set of data that how can I use it in a way that is providing geological information, and it seems to me that it hasn't matured as part of the industry yet. There's still plenty of places for innovation and the production of making a product production code rather than experimental code. And that was it. Thank you very much.
Thank you.
No, this is an airborne EM plane. Another one of the aircraft that I've flown surveys in. So thank you very much for your attention.
Thank you, Mike.
Thank you for your presentation, Mike.
So do we want to?
So I think we don't need to do question and answer parts because we basically do it during the meeting, right?
Yep.
So if you guys have any question, you can ask now. Mike's here. Otherwise,
if you think of something, just email me a question and I can look into it offline for you as well.
Thank you very much, Mike.
Thank you so much, Mike.
That's okay.
I have a question.
Oh, yeah.
In Australia, do you have any FTG data on Australia?
In Australia, do we have any FTG data?
Yeah.
Yes, we do. They're starting to collect it now, and there are some FTG data sets that are available from the state governments. I think in the Northern Territory, they're actually flying a large FTG survey now. So that will become available to the public eventually.
In Western Australia?
Yeah, there will be FTG data and probably Falcon data surveys available. You just have to check with the Western Australian Geological Survey.
Okay.
It's not as well curated as the magnetics and radiometrics and gravity because it's not a national coverage, it's just bits and pieces. So if you go to the state geological surveys, to their websites, Geological Survey Western Australia, Northern Territory, Queensland, you can usually search on those websites for the data, and if it's freely available, download it.
Yeah. Free. I can show you the website.
Yeah, free. If it's there, if it's open file and the companies have finished using it, then the state provides it free.
Yeah. Yeah. Yeah.
So if you want to have other data sets to play with, you can.
So the Australian legislative domain means when you get an exploration license, time expires, but you have to hand the data you've acquired back into the public domain to support further exploration. Basically, that's what happens.
Dr. Zuhar, do you have any question for us?
I reserve for tomorrow.
You're flying off what time?
I'm flying tonight 10 and then should be arriving there around 9 morning. 9:15 or something like that.
Okay.
Are you directly coming to Brighton or?
Depend on Sean. He's arranging my.
Yeah. Okay. Sean is arranging your trip to Sydney. Okay. Cool. Okay. Good.
Okay.
Thank you so much, everyone.
Thank you very much, guys. I enjoyed today a lot. Thank you.
Thanks, Mike.
See you tomorrow, Dr. Zuhar.
reply.
See you. Yeah.
Thanks, Mike.
We should
See you
make the
tomorrow.
session tomorrow go later, so